What if everything we see, everything we touch, everything we think we understand about the universe is just a fraction of the full picture? Picture standing at the edge of an endless ocean, staring at the surface, while beneath it lies a world of unimaginable depth and complexity. That's where we find ourselves when we talk about the hidden dimensions of the cosmos, layers of reality so profound they defy our everyday experience. For centuries, we've looked to the stars and wondered about the nature of existence, but today, we're on the brink of discoveries that could shatter our perception of reality itself. This isn't just science fiction, it's the cutting edge of physics, where theories about hidden dimensions aren't just wild guesses, but serious attempts to answer the universe's biggest questions. Think about the last time you felt that spine-tingling sense of wonder, the kind that makes you question everything. That's the feeling we're chasing as we explore 40 of the most mind-bending theories about the universe's hidden dimensions. From the elegant twists of string theory to the audacious idea of parallel worlds brushing against our own, these concepts don't just challenge our understanding, they rewrite it. Imagine dimensions curled up so tightly they're invisible to us, or entire universes existing just beyond our perception, separated by the thinnest veil of space-time. These aren't just abstract ideas, they're clues to a puzzle that could reveal why the cosmos works the way it does, and whether we're truly alone in it. So why should any of this matter to you? Because hidden within these theories are answers to questions humanity has asked since the dawn of time. What is reality made of? Are there other versions of us out there? And what lies beyond the limits of our perception? This journey isn't just for physicists, it's for anyone who's ever looked up at the night sky and felt that pull of curiosity, that hunger to know more. Over the next 40 theories, we'll venture into the unknown, where the rules of physics bend and the universe reveals its deepest secrets. Buckle up, because what you're about to discover will change the way you see everything. At the core of string theory is a revelation that would make even the most imaginative science fiction writers pause. Our universe might be woven from tiny, vibrating strings, each oscillation giving rise to the particles that make up everything from stars to human beings. But here's the twist: these strings don't dance in just the 3 dimensions we know. They vibrate through as many as 10 or 11 dimensions, all curled up like microscopic origami, hidden from our everyday perception. Think of it like an ant crawling across a tightly rolled up piece of paper. It moves along the surface, completely unaware of the larger structure. That ant is us and the paper. It's the hidden fabric of reality. What makes this idea so revolutionary isn't just the extra dimensions themselves, but what they could explain. For decades, physicists have struggled to reconcile gravity, the force that shapes galaxies, with the bizarre rules of quantum mechanics, which govern the subatomic world. String theory suggests that these hidden dimensions might be the missing link, the secret handshake between the very large and the unimaginably small. It's as if we've been trying to solve a cosmic jigsaw puzzle with half the pieces missing, and now we're finally glimpsing where they might fit. But how do you prove something you can't see? That's where the world's most powerful particle colliders come in. By smashing particles together at nearly the speed of light, scientists hope to catch a fleeting glimpse of energy escaping into these extra dimensions, like a whisper echoing through a hidden corridor. Others are scouring the cosmos for tiny deviations in gravity's strength, which could hint at dimensions bending space-time in ways we're only beginning to understand. The challenge is staggering, but the payoff could be nothing less than a unified theory of physics, a single framework that explains everything from the birth of black holes to the flicker of a quantum particle. Yet for all its elegance, string theory remains controversial. Some argue it's more math than science, a beautiful idea without experimental proof. But that's the thrill of exploration. Sometimes the boldest ideas take decades, even centuries, to reveal their truth. Whether string theory ultimately holds the answers or simply lights the way to something even stranger, one thing is certain: the universe is far more intricate, far more mysterious than we ever dared to dream. And that's just the first theory. The holographic principle turns everything we think we know about reality inside out. Imagine the entire universe, every galaxy, every atom, every fleeting thought, as nothing more than a shimmering projection, like a three-dimensional movie cast from information etched onto a flat, distant surface. It sounds like something ripped from the pages of a sci-fi novel, but this idea emerges from the cold, hard math of black hole physics. When scientists calculated how much information could fit inside a black hole's event horizon, they stumbled onto something astonishing. The maximum data it could hold wasn't determined by its volume, but by its surface area. It's as if the universe itself was whispering a secret reality might not be built from depth, but from a cosmic code written on its edges. Take a hologram as an everyday analogy. That credit card sticker with a floating eagle, the image appears to have thickness, shadows, even movement, but lift it to the light, and you'll find it's just a flat, patterned film. The holographic principle suggests our universe operates the same way. All the richness we experience, the swirl of a nebula, the warmth of sunlight, the complexity of human consciousness, could be data processed from a two-dimensional boundary we'll never see. Even stranger, this might solve one of physics' greatest puzzles: how to reconcile Einstein's smooth, continuous space-time with the pixelated, quantum nature of reality. If the universe is a projection, its resolution could explain why gravity and quantum mechanics clash. They're literally speaking different dimensional languages. Black holes might be the key to testing this radical idea. These cosmic vacuums don't just swallow matter, they compress information into an unimaginably dense imprint on their event horizons. Some theorists argue that when matter falls in, it isn't truly destroyed, it's smeared across the surface like cosmic ink, preserving every detail in scrambled form. If we could somehow decode that information, it would be like finding the universe's original blueprint. Already, experiments with ultra-precise lasers are hunting for pixelation in space, time itself, tiny irregularities that might betray the illusion of a higher dimensional world. Yet the implications stretch far beyond equations. If the holographic principle holds, it redefines what it means to exist. Are we just shadows on a wall, or is the wall itself a kind of existence we've yet to comprehend? It challenges the very notion of location, your body, your memories. Even this video might be processes unfolding on a boundary billions of light years away. And if information is truly fundamental, it raises haunting questions. Is reality more like a simulation, or a language we're only beginning to decipher? One thing's certain: the universe just got a lot weirder, and we're only scratching the surface. What if our entire universe is just one page in a cosmic book, floating alongside countless other pages we can't see? That's the mind-bending premise of brane-world scenarios, where our reality isn't a standalone universe but a membrane, or brane, adrift in a higher dimensional space. Think of it like a slice of bread in an infinite loaf, with other branes stacked invisibly close, separated by dimensions we're utterly blind to. These parallel membranes could be mere millimeters away in a direction we can't point to, filled with their own stars, their own laws of physics, even their own versions of us. And when these branes collide, the energy released might be enough to birth entire universes, including perhaps our own Big Bang. This isn't just wild speculation. The math behind M-theory, the grander framework that unites string theory's tangled threads, suggests gravity behaves oddly because it's the only force that can leak between branes. Picture a flashlight shining through layers of fabric gravities. Glow dims as it seeps into other dimensions, which could explain why it's so weak compared to electromagnetism or nuclear forces. It's as if we've been trying to study a shadow while missing the object casting it. The most tantalizing clue might come from gravitational waves. When black holes merge, they send ripples through space-time. But if some of those ripples vanish into extra dimensions, detectors like LIGO could spot anomalies in the signal. It'd be like hearing an echo in a room with hidden doors, proof of spaces beyond our perception. Some theorists even propose that dark matter, the invisible glue holding galaxies together, could be ordinary matter trapped on a neighboring brane, its gravity bleeding into ours. Yet the implications go beyond physics. If branes drift and collide cyclically, our universe might be one chapter in an endless cosmic saga, with each collision resetting the clock. Are we living in the aftermath of a brane collision, destined to meet another membrane in the distant future? The answer could rewrite not just our understanding of the cosmos, but our place within it. And the tools to find out might already be in our hands, quietly listening to the whispers of gravity. If you've ever watched an ant crawl along a telephone wire, you've glimpsed the strange reality of compactified dimensions, even if you didn't realize it. From a distance, that wire looks like a simple line, a one-dimensional thread stretching across the sky. But to the ant, it's a vast, curved landscape with room to circle around, even disappear from view if it loops to the other side. That's the essence of compactification, dimensions so tightly curled, so unimaginably small, that to creatures like us bound by the limits of our perception, they might as well not exist at all. Yet these hidden folds could be the reason why particles have mass, why forces like electromagnetism and gravity behave so differently, and ultimately, why the universe works the way it does. The math behind this idea is as beautiful as it is bizarre. Picture a Calabi-Yau manifold, a six-dimensional shape so complex, even supercomputers struggle to visualize it. These twisting, hyperdimensional geometries could be the scaffolding of reality itself, with every knot and curve influencing how particles vibrate. Imagine a cosmic piano where the strings are invisible dimensions, and every note they play determines the properties of matter. An electron's charge, a quark's spin, even the Higgs boson's mass, all might arise from the secret symphony of these folded spaces. But how do you hunt for dimensions smaller than a quark? The answer lies in the quantum realm, where particles don't play by ordinary rules. If extra dimensions exist, they'd leave fingerprints in the energy of colliding particles, tiny discrepancies that can't be explained by three-dimensional physics. It's like throwing a ball in a room you think is empty, only for it to bounce slightly off course, hinting at furniture you can't see. Experiments like the Large Hadron Collider are designed to catch these anomalies, probing energies so high they might briefly uncurl hidden dimensions, revealing their influence. Yet the most tantalizing clue might come from something far older: light. If photons, particles of light, leak into extra dimensions as they travel across the cosmos, their energy could subtly drain over billions of years. Telescopes are now scanning distant quasars for signs of this dimming, a potential whisper from dimensions beyond our own. Whether these folds are real or not, one thing's clear: the universe has a knack for hiding its most profound secrets in the smallest of places. And if we're right, the key to unlocking them might already be in our hands. the idea of a multiverse isn't just science fiction, it's a serious scientific possibility that could explain why our universe seems so finely tuned for life. Imagine a frothing ocean of space-time where new universes bubble into existence endlessly, each with its own unique recipe of dimensions, physical laws, and fundamental constants. Some might have 6 spatial dimensions, others none. Some could be ruled by gravity 1,000 times stronger than ours, while in others, atoms might never form at all. This is the wild landscape of bubble universes, a consequence of cosmic inflation, the same theory that explains the rapid expansion of our own universe after the Big Bang. Here's how it might work. Picture a pot of water boiling violently, with steam bubbles forming and rising to the surface. In this analogy, the boiling water is a higher dimensional parent space, and each steam bubble is a newborn universe, pinching off into its own isolated reality. Our entire cosmos could be one such bubble, floating in an unimaginably vast multiverse where the laws of physics are as variable as the weather. This isn't just poetic speculation. The math behind eternal inflation suggests that once inflation starts, it never truly stops, creating an endless cascade of universes with every possible configuration. But if these other universes are forever out of reach, how could we ever know they exist? The answer might lie in the oldest light in the cosmos, the cosmic microwave background, the afterglow of the Big Bang. If our bubble universe ever collided with another in the distant past, the shockwave could have left a faint imprint, a strange, circular pattern in the microwave background that defies conventional explanation. Astronomers have already spotted a few tantalizing anomalies like the infamous cold spot, where temperatures dip unexpectedly in a way that could hint at a brush with another universe's edge. It's like finding a fingerprint on a window pane, evidence of something pressing against the glass from the other side. The implications are staggering. If bubble universes are real, they could solve one of physics' deepest mysteries: why our universe seems so improbably perfect for life. With infinite variations playing out across the multiverse, it's no surprise that at least one universe, ours, got lucky with the right conditions. But it also raises haunting questions. Are there other versions of us out there, living in universes where gravity is weaker or time runs backward? Could advanced civilizations in neighboring bubbles even detect us, or are we forever separated by the unbridgeable gaps of higher dimensional space? The search for answers is already underway. Next-generation telescopes and quantum sensors are being designed to scour the cosmic microwave background for more clues, while theorists refine their models to predict what a bubble collision should look like. Whether the evidence arrives in our lifetime or not, one thing is certain: the universe is far stranger, far more expansive than we ever dreamed, and the most breathtaking part: we might just be one tiny bubble in an infinite cosmic sea. Long before string theory or brains entered the scientific spotlight, a quiet revolution was brewing in the mind of mathematician Theodore Kaluza. In 1921, he sent a letter to Albert Einstein that would change physics forever, proposing a radical idea that electromagnetism, the force behind light and electricity, wasn't just a fundamental law of nature, but a shadow cast by a hidden fifth dimension. Picture a world where gravity and electricity aren't separate forces at all, but different faces of the same phenomenon, unified by a dimension too small for our eyes to see. That's the elegance of Kaluza-Klein theory, a concept so ahead of its time, it took decades for the world to catch up. Here's how it works. Imagine space isn't just length, width, and height, but has a fourth spatial dimension curled up like a microscopic loop. Just as a garden hose looks like a line from far away but reveals its cylindrical shape up close, this fifth dimension could be compactified, so tiny its effects only appear in the quantum realm. Kaluza showed that when Einstein's equations for gravity were written in 5 dimensions, an extra term emerged that perfectly described Maxwell's equations for electromagnetism. It was as if the universe had been whispering its secrets in a hidden language, and Kaluza had just deciphered the first word, yet the theory hit a snag. Physicist Oscar Klein later refined the math, suggesting this extra dimension might be smaller than an atom. But if that were true, why hadn't we detected it? The answer lies in the energy required to see such scales. Think of it like trying to spot a single pixel on a stadium-sized screen. Without tools powerful enough to resolve such fine detail, the dimension remains invisible. For decades, the idea languished, overshadowed by quantum mechanics and later string theory. But here's where it gets fascinating. Modern physicists are revisiting Kaluza-Klein with fresh eyes, realizing its simplicity might hold clues that more complex theories have overlooked. Recent work in particle physics hints that extra dimensions could explain why the Higgs boson is so surprisingly light, a puzzle known as the hierarchy problem. If the Higgs interacts with fields in hidden dimensions, its mass might be diluted, like ink spreading through folded paper. Others speculate that dark matter could be ordinary matter trapped in a higher dimensional mirror world, with Kaluza-Klein particles serving as bridges between realms. Even gravitational waves might carry traces of these dimensions' subtle vibrations that could betray their presence in data from observatories like LISA. What makes Kaluza-Klein theory so enduring isn't just its mathematical beauty, but its humility. It reminds us that breakthroughs often come from asking deceptively simple questions. What if there's more to space than we can perceive? What if forces we think are separate are actually woven together in higher dimensions? While string theory and brains dominate today's discussions, the ghost of Kaluza's 5th dimension lingers, a testament to the power of an idea whose time may still be coming. After all, the history of science is filled with concepts dismissed too soon, only to resurface when the world is finally ready to listen. Picture space-time not as a flat stage where events unfold, but as a dynamic, warped fabric, one that bends and twists under the weight of stars and galaxies. Now take that curvature and stretch it into higher dimensions where the folds become so extreme they act like cosmic valleys, trapping gravity itself. This is the bold vision of warped dimensions, a theory that reshapes our understanding of reality by suggesting the very fabric of space isn't just bent. It's sculpted in ways that hide entire layers of the universe from view. At the heart of this idea is a paradox. Gravity, the force that binds galaxies together, is astonishingly weak compared to other fundamental forces. A fridge magnet can defy Earth's gravitational pull with ease, lifting a paperclip against the weight of an entire planet. Why Lisa Randall and Raman Sundram proposed a radical answer: gravity isn't feeble. It's just diluted, spilling into hidden dimensions we can't access. Their model imagines our universe as a membrane floating in a higher dimensional space, with gravity's influence concentrated near our brain like ripples trapped in a shallow pond. The rest of gravity's strength, it's lost in the warp and weft of dimensions curled into shapes so extreme they're effectively invisible. The math behind this is as elegant as it is mind-bending. Imagine 2 parallel sheets of paper representing branes, separated not by empty space, but by a dimension that warps exponentially, like a valley so deep, its walls curve sharply inward. Gravity, bound to the distant brane, would appear weak to us, its signal fading as it traverses the warped geometry. This isn't just theoretical sleight of hand. It could explain why the Higgs boson's mass is so puzzlingly low, or why dark energy's influence is so subtle. The warps act like a cosmic filter, muffling forces that might otherwise overwhelm our universe. But how do you test something so abstract? Particle colliders offer one clue. If warped dimensions exist, high-energy collisions might produce Kaluza-Klein gravitons particles that briefly tunnel through the hidden geometry before snapping back, leaving telltale gaps in energy signatures. Another hint could come from gravitational waves. Subtle distortions in these ripples of space-time might reveal the echo of warped dimensions bending their path. Even everyday gravity experiments are joining the hunt, with ultra-sensitive devices measuring its strength at microscopic scales, searching for deviations that could betray hidden curvature. The most thrilling possibility, though, is what lies beyond the warp. If gravity can leak into higher dimensions, could entire universes exist just past the fold? Some models suggest other branes might hover mere millimeters away in a fifth dimension, forever invisible because light and matter are stuck to their own membranes. A civilization there could be close enough to touch if only we could reach through the dimensional divide. It's a humbling thought. The cosmos might be far more crowded than we ever imagined, with realms separated not by distance, but by the hidden architecture of space itself. What makes warped dimensions so compelling isn't just their explanatory power, it's their audacity. They challenge us to rethink the very nature of reality, suggesting that the universe's deepest secrets aren't written in particles or forces, but in the invisible folds of dimensions we're only beginning to map. And if Randall and Sundram are right, the answers we're seeking might not lie in distant galaxies, but in the warped geometry right beneath our feet, or rather, in directions we can't even point to. The universe, it seems, still has a few twists left to reveal. Dark matter has long been the universe's most frustrating riddle, an invisible something that makes up 85% of all matter, yet refuses to interact with light or ordinary particles. But what if we've been searching in the wrong dimension? A daring theory proposes that dark matter isn't some exotic particle we've yet to discover, but something far stranger, ordinary matter vibrating in dimensions we can't access. Picture a world where every star, every planet, every speck of dust has a twin, not an anti-particle or a parallel version, but a higher dimensional counterpart moving through reality at angles we can't perceive. To us, these shadows would appear only through their gravitational pull, like footsteps in an empty room. This idea flips conventional dark matter research on its head. Instead of hunting for weakly interacting particles in underground labs, physicists could be staring at the answer all along, hidden in plain sight, or rather, hidden in directions our senses can't follow. Think of it like a two-dimensional creature living on a sheet of paper, unaware that the mysterious forces it feels are just the weight of objects stacked above it in the third dimension. In our case, the extra dimensions could be so tightly wound or warped that only gravity spills across the divide, leaving no other trace. It's a cosmic game of hide and seek where the hider isn't just invisible, they're playing by rules we don't even know exist. The math behind this is surprisingly elegant. Just as vibrations on a guitar string can produce different notes, matter oscillating in extra dimensions would have unique energy signatures. Some models suggest these higher dimensional particles could appear as towers of increasingly massive states in our three-dimensional world, each one a rung on a ladder leading to unseen realms. Experiments like the Large Hadron Collider might already be creating these particles, their fleeting existence chalked up to background noise. But if researchers could tease out these patterns, it would be like finding a message scrawled in the margins of reality itself. Even more tantalizing are the cosmological clues. Galaxies rotate faster than they should, and galaxy clusters bend light more than visible matter can explain phenomena we blame on dark matter. But if gravity from higher dimensional matter is leaking into our universe, it could account for these anomalies without inventing new particles. Some theorists argue that certain gravitational wave signals, tiny hiccups in the fabric of space-time, could carry imprints of these hidden dimensions, like echoes bouncing between walls we can't see. The implications are staggering. If dark matter is just matter in extra dimensions, it would mean we're surrounded by an entire shadow universe, intertwined with ours but forever out of reach. Civilizations could thrive there, stars could burn, and black holes could collide, all unseen, all detectable only by the faintest tug on our reality. It's a humbling thought. The universe's greatest mystery might not be about what's missing, but where we're not looking. And the tools to find out might already be in our hands if we dare to reinterpret the data through the lens of dimensions beyond. Quantum entanglement has baffled scientists since Einstein famously called it spooky action at a distance, the eerie phenomenon where two particles become linked, instantly mirroring each other's states no matter how far apart they are. But what if this quantum weirdness isn't just strange behavior in our three-dimensional world? What if entangled particles are actually whispering to each other through hidden dimensions, bypassing space as we know it entirely? Imagine two ants crawling on opposite ends of a folded piece of paper. To us, they're separated by inches, but if the paper bends in a higher dimension, they could be touching without realizing it. That might be how entanglement works. Particles so deeply connected, they're essentially next-door neighbors in directions we can't see. This idea flips the script on conventional explanations. Instead of breaking the cosmic speed limit by communicating faster than light, entangled particles might not need to communicate at all. Their connection could be woven into the fabric of higher dimensional space, where separation is an illusion. Think of it like a pair of gloves, one left-handed, one right-handed. In our world, they're opposites, but rotate them through a fourth spatial dimension, and they become identical. Similarly, particles might appear mysteriously linked because their true relationship exists outside our limited perception. The math behind this is as elegant as it is mind-bending. Some string theory models suggest that entangled particles could be ends of the same fundamental string, vibrating through extra dimensions, like a cosmic thread passing through the eye of a needle we can't locate. Others propose that quantum waves, the probability clouds defining a particle's position, might ripple through hidden geometries, allowing instantaneous correlations. If true, this would mean the spookiness Einstein resisted isn't a flaw in quantum mechanics, but a clue pointing to reality's full, multidimensional nature. Experiments are already hinting at this possibility. When physicists measure entangled photons, the correlations between them are stronger than any three-dimensional model can explain, as if something unseen is amplifying their connection. Future quantum labs could test this directly by entangling particles in controlled environments, then probing for subtle anomalies in their behavior. One approach involves quantum drums, tiny vibrating membranes cooled to near absolute zero. If these drums stay synchronized in ways that defy three-dimensional physics, it could suggest whispers from extra dimensions. The implications stretch far beyond the lab. If entanglement rides on hidden dimensions, it might revolutionize how we envision everything from black holes to the birth of the universe. Some theories suggest the entire cosmos was once a single, infinitely entangled quantum state, and that higher dimensions preserved those connections as space expanded. Others speculate that advanced civilizations could harness dimensional entanglement for communication, sending messages across galaxies without delay. Of course, not all physicists are convinced. Skeptics argue that invoking extra dimensions to explain quantum mechanics is like using a sledgehammer to crack a walnut, an overcomplication when simpler theories might suffice. But that's the beauty of science. The wildest ideas often lead to the deepest truths. Whether entanglement's secret lies in unseen dimensions or something even stranger, one thing's clear: the universe still has cards up its sleeve, and we're only beginning to peek at the hand it's holding. Time isn't just a ticking clock or a relentless forward march. It might be a dimension with hidden depths we've barely begun to explore. We're used to thinking of it as the fourth dimension, woven together with space in Einstein's fabric of reality. But what if time itself has layers, folds, even branches we can't perceive? Imagine a river splitting into countless tributaries, each flowing at its own pace, some looping back on themselves like cosmic whirlpools. That's the daring idea behind time as a higher dimension, a concept that doesn't just redefine clocks and calendars, but could unlock the most tantalizing possibility of all: time travel. Take closed time-like curves, for example. These aren't sci-fi plot devices but serious solutions to Einstein's equations: paths through space-time that curve so sharply they circle back to their own past. Picture a hiker ascending a mountain only to find their own footprints already in the snow. In a universe with higher dimensional time, such loops might not be paradoxes but natural features, like eddies in a stream. The catch: these curves likely require extreme conditions: black holes with near-infinite spin, or cosmic strings thinner than an atom but with the mass of a galaxy. Yet if hidden dimensions exist, they could warp time in ways that make these phenomena far more accessible than we thought. Here's where it gets stranger. Some models suggest that what we experience as a single, uniform now might be a shadow of richer temporal dimensions, like a two-dimensional movie screen trying to depict a three-dimensional world. In higher dimensional time, multiple nows could coexist, branching and merging like threads in a tapestry. This wouldn't just explain time's elusive flow. It might resolve quantum mechanics' infamous measurement problem, where particles seem to exist in multiple states until observed. Could collapse into a definite state just be our limited perspective, like a flatlander perceiving only a slice of a spinning top? The implications are dizzying. If time has hidden dimensions, causality, the bedrock of physics, might be more flexible than we imagined. Events could influence each other not just linearly, but through folds in temporal geometry, like notes passed through a crumpled piece of paper. Wormholes, often imagined as spatial shortcuts, might also be temporal bridges, their mouths connected not just by distance but by higher dimensional time. Even dark energy's mysterious acceleration of the universe's expansion could stem from time's unseen architecture, like a clock spring unwinding in directions we can't measure. Of course, the paradoxes loom large. If time travel is possible, why haven't we met tourists from the future? Maybe because higher dimensional time isn't a free-for-all but a structured landscape, with branches that prevent contradictions, like a river that splits but never flows backward. Or perhaps time travelers are all around us, hidden in dimensions our senses can't access. The truth might lie in experiments already underway, atomic clocks precise enough to detect subtle time warps, or gravitational wave observatories hunting for ripples that carry echoes of temporal folds. What makes this theory so electrifying isn't just its potential to explain the unexplainable, it's the way it turns our most intimate experience of reality inside out. Time isn't just something we move through. It might be something we're embedded in, like characters in a book unaware of the hands turning the pages. And if physicists are right, those hands might be reaching from dimensions we're only beginning to imagine. The Big Bang might be the most famous origin story in science, but what if it wasn't the beginning at all? Enter the Echperotic Universe, a theory so audacious, it rewrites cosmic history not with a bang but with a crash. Picture two colossal membranes floating like sheets of paper in a higher dimensional space, slowly drifting toward each other. When they collide, the energy unleashed doesn't destroy, it creates not just stars or galaxies, but an entire universe, complete with its own laws of physics and arrow of time. This isn't a one-time event. According to the Echperotic model, our cosmos is just one chapter in an endless cycle of collisions, expansions, and rebirths, each resetting the cosmic clock without a true beginning or end. What makes this idea so compelling is how neatly it solves some of cosmology's stickiest puzzles. Take the horizon problem. The fact that distant regions of the universe are eerily similar in temperature, despite never having had time to exchange heat. Inflation theory explains this by proposing a faster-than-light expansion in the universe's first moments. But the Echperotic model offers a different answer. Those regions were once touching, part of the same flat, cold brane before the collision stretched them apart. It's like smoothing out a crumpled bedsheet before folding it again. The wrinkles of uneven heat distribution never get a chance to form. Then there's the question of dark energy. If the universe cycles endlessly, the accelerating expansion we observe today might not be a mysterious force but a signpost, the quiet stretch before the next collision. Imagine a rubber band pulled taut, storing energy until it snaps back. In this view, dark energy isn't a cosmic anomaly. It's the prelude to the next act. Even the universe's startling flatness, its lack of obvious curvature, fits the model. Each collision irons out spatial wrinkles, leaving behind a universe that appears finely tuned by sheer repetition. But how could we ever test such a radical idea? The smoking gun might lie in gravitational waves. Unlike the chaotic ripples predicted from a Big Bang singularity, an echperotic collision would produce a cleaner signal, a specific pattern of waves that future observatories like the Laser Interferometer Space Antenna LISA could detect. Others are scouring the cosmic microwave background for exotic signatures, like imprints from defects in the branes themselves. Even the Large Hadron Collider plays a role. If extra dimensions exist, high-energy collisions might briefly reveal their presence, offering indirect support for the brane-world framework. Yet the most mind-bending implication isn't scientific, it's philosophical. If the Echperotic model holds, time itself loses its linear narrative. There's no definitive starting point, no heat death of the universe, just an infinite dance of creation and destruction. Civilizations could rise and fall across countless cycles, their histories erased by each new collision, their achievements lost to the cosmic reset. It's humbling to think that everything we know, every galaxy, every atom, every moment of human history, might be just one iteration in an endless loop, a single note in a symphony with no finale. Of course, not all physicists are convinced. Critics argue that the model requires brains to approach each other with near-perfect alignment, a fine-tuning problem of its own. Others question whether a collision could ever produce the uniformity we observe, but that's the beauty of science at the frontier. The boldest ideas force us to ask better questions. Whether the Echperotic universe ultimately triumphs or falls, it reminds us that the cosmos might be stranger, grander, and more cyclical than we ever dared to dream. And if we're right about the cycle, the next collision could already be on its way, hurtling toward us from dimensions we've yet to perceive. Supersymmetry isn't just a clever idea, it's a mathematical symphony so elegant, it could rewrite the rules of the universe. At its core lies a simple but profound proposition. Every particle we know, from the humble electron to the elusive neutrino, has a hidden twin, a superpartner with wildly different properties. These twins aren't just theoretical flourishes, they could solve some of physics' biggest headaches, like why the Higgs boson is so lightweight compared to gravity's staggering strength. But here's the twist. Despite decades of searching, we've found zero evidence of these superpartners. So where are they? The answer might lie beyond the dimensions we can see. Imagine throwing a ball into the air, only for it to vanish mid-flight. That's essentially what's happening with supersymmetry's missing particles, except the vanishing act might occur because they're moving through dimensions curled up tighter than a clenched fist. In string theory, these extra dimensions aren't just empty space. They're dynamic landscapes where particles could gain mass or even hide by vibrating in ways we can't detect. Superpartners might be all around us, their effects leaking into our world only as faint gravitational whispers. It's like living next to a concert hall with walls so thick you only feel the bass, never hearing the full melody. The stakes couldn't be higher. If supersymmetry is real, it wouldn't just confirm hidden dimensions, it would bridge quantum mechanics and gravity, two frameworks that currently refuse to play nice. Picture two groups speaking different languages. Supersymmetry could be the universal translator, revealing a deeper grammar underpinning reality. Experiments at the Large Hadron Collider are hunting for superpartners by smashing protons at nearly light speed, hoping to catch a glimpse of energy bleeding into extra dimensions. Even a single detection could send shockwaves through physics, proving that the universe is far more interconnected than we ever imagined. Yet skeptics argue that supersymmetry's elegance might be its downfall. With no superpartners found despite increasingly sensitive searches, some wonder if we're chasing a beautiful mirage. Others propose radical alternatives like split supersymmetry, where only certain particles have twins or folded dimensions so warped they distort our observations entirely. The debate rages on, but one thing's certain: whether supersymmetry survives or falls, it's pushing us to ask better questions about the fabric of reality. What makes this theory so thrilling isn't just its potential to solve puzzles, it's the sheer audacity of its vision. If confirmed, we wouldn't just be adding new particles to the cosmic inventory, we'd be uncovering layers of existence previously reserved for philosophy or fantasy. The universe might be teeming with unseen partners, dancing just beyond the reach of our detectors, waiting for the right experiment or the right dimension to reveal their secrets. And when they do, the story of physics won't just gain a new chapter, it'll rewrite the entire book. Gravity is the force that holds galaxies together, yet it's astonishingly feeble compared to the other fundamental forces. A simple fridge magnet can defy the pull of an entire planet, lifting a paperclip with ease. This bizarre mismatch isn't just a quirk, it's one of physics' most perplexing riddles, known as the hierarchy problem. Why should gravity be so unimaginably weaker than electromagnetism or the nuclear forces? The answer might not lie in our three-dimensional world at all, but in the hidden folds of reality itself, dimensions we can't see, where gravity's true strength is spilling away like water through a sieve. Picture a campfire on a cold night. Stand close and the heat is intense, almost overwhelming, but step back just a few feet and the warmth fades to a faint whisper. Now imagine that campfire is gravity, and the space it's radiating through isn't just the air around you, it's a higher dimensional landscape, with gravity's influence diffusing into directions we can't point to. This is the radical idea behind the hidden dimension solution to the hierarchy problem. Gravity isn't inherently weak, it's just diluted, stretched thin across dimensions curled up smaller than an atom. While other forces like electromagnetism remain trapped in our familiar three-dimensional brane, gravity leaks out, its full strength visible only to creatures who could perceive these extra directions. The math behind this is as elegant as it is mind-bending. In some models, these extra dimensions aren't tiny, uniform curls but vast, warped landscapes like a funnel where gravity's intensity drops off dramatically as you move away from our brain. Think of it like a mountain climber shouting into a valley. From the peak, their voice carries far, but down in the gorge, the sound is muffled, almost lost. Similarly, gravity might appear weak to us because we're stuck in the valley of a higher dimensional geometry, while its true power resonates elsewhere. Experiments are already hunting for clues. Particle colliders like the Large Hadron Collider could produce miniature black holes, brief, unstable ones if extra dimensions exist at certain scales. These wouldn't devour the Earth despite alarmist headlines, but would vanish in a flash of radiation, leaving behind a signature that screams higher dimensions. Other researchers are scrutinizing gravity's behavior at microscopic distances, where deviations from Newton's familiar inverse square law might betray hidden dimensions warping its pull. Even gravitational waves could carry imprints of these unseen realms, subtle distortions in their ripples that hint at gravity's full multidimensional nature. But the implications go deeper than particle physics. If hidden dimensions explain gravity's feebleness, they might also hold the key to unifying all forces under one framework, a dream physicists have chased since Einstein. It's like realizing that the scattered pieces of a jigsaw puzzle aren't missing. They're just hiding in a drawer you never thought to check. And if we're right, the universe isn't just stranger than we imagined. It's stranger than we can imagine, with gravity's true might lurking in dimensions waiting to be discovered. The most humbling thought, we might be like flatlanders, oblivious to the heights and depths around us, mistaking a shadow for the whole. Gravity's weakness isn't a flaw in the cosmos. It's a fingerprint of reality's hidden architecture, a clue that the universe has been keeping secrets far grander than we ever suspected. And the tools to uncover them might already be in our hands, if we dare to look beyond the dimensions we know. Black holes have long been the ultimate cosmic enigmas, regions of space where gravity is so intense, not even light can escape. But what if these terrifying voids aren't just dead ends? What if, instead of crushing matter into oblivion, they serve as bridges to realms beyond our universe? This is the spine-tingling possibility that some physicists are now seriously considering. That black holes might be higher dimensional portals, their unfathomable cores not singularities at all, but wormholes threading through hidden dimensions like cosmic subway tunnels. Picture this, you're floating toward a black hole's event horizon, that point of no return where time and space twist beyond recognition. Conventional wisdom says you'd be stretched into spaghetti by tidal forces, your atoms shredded into quantum confetti. But in certain theoretical models, that horizon might be a veil, not a wall. Beyond it, the black hole's crushing gravity could warp space-time so severely, it punches through into another dimension, or even another universe entirely. Think of it like a sheet of paper folded in half with a pencil stabbing through the layers. To a two-dimensional creature living on the paper's surface, the whole would appear as a mysterious circle with no exit. But in 3 dimensions, it's a passageway. Could black holes be doing the same thing, just on a cosmic scale? The math behind this idea comes straight from Einstein's equations. Wormholes' hypothetical shortcuts through space-time have been hiding in general relativity for over a century, often dismissed as mathematical oddities. But when you introduce extra dimensions, these tunnels stop being mere curiosities and start looking like plausible features of reality. Some string theory models suggest that black holes and wormholes might be 2 sides of the same coin, their differences depending entirely on perspective. From our 3-dimensional viewpoint, a black hole's core looks like a singularity, a point of infinite density. but from a higher dimensional angle, it could be the mouth of a tunnel, its other end opening into a distant universe or a different epoch of time. How could we ever test such a wild idea? Surprisingly, astronomers might already have clues. When black holes merge, they send gravitational waves rippling through space-time, and the patterns in those waves could carry subtle hints of what's happening inside. If a black hole's interior isn't a singularity but a wormhole throat, the waves might exhibit faint echoes like sounds bouncing down a long corridor. Some researchers claim they've spotted these very echoes in data from LIGO, though the debate is far from settled. Others are studying the bizarre orbits of stars near supermassive black holes, looking for anomalies that might betray the presence of hidden geometry. Of course, the risks of diving into a black hole, even a hypothetical wormhole, remain astronomical. The tidal forces, radiation, and sheer unpredictability of quantum effects make it a one-way trip with no guarantees. But the philosophical implications are irresistible. If black holes are portals, our universe might be part of an unimaginably vast network, each hole a stitch in the fabric of a multiverse. Civilizations could theoretically use them to traverse impossible distances, or even to send messages backward in time. The most humbling thought, we might already be surrounded by these gateways, their secrets locked behind horizons we can't cross. The universe, it seems, has a flair for the dramatic, hiding its most astonishing possibilities in the darkest corners of space, waiting for us to shine a light where no one has looked before. And if we're right, the greatest adventures might not lie in the stars we see, but in the voids we've yet to understand. String theory doesn't just suggest hidden dimensions, it paints a picture of a cosmic landscape so vast, our entire universe might be just one lonely hilltop in an endless mountain range. Imagine standing in a library where every book isn't just a story, but an entire reality with its own rules. Some universes have 6 dimensions, others 10. Some have gravity 1,000 times stronger, while in others, atoms could never even form. This is the staggering vision of the string theory landscape, a megaverse of possibilities where the constants we take for granted, like the speed of light or the charge of an electron, might just be local quirks of our particular corner of existence. But how does this work in practice? Think of the universe like a ball resting in a valley. The shape of the land, the hills and valleys of higher dimensional space determines the laws of physics that emerge. Our universe happens to sit in a valley where the numbers line up just right for stars, planets, and life. But elsewhere in the landscape, there could be valleys where gravity crushes everything instantly, or where matter is so unstable, nothing lasts longer than a blink. It's like tuning a radio. Most stations are static, but every so often you hit a frequency where everything clicks into place. The eerie part, if even one of our universe's constants were slightly different, if the strength of gravity or the mass of quarks shifted by a hair, life as we know it would be impossible. This raises a haunting question. Are we here by pure luck, or is there something special about our place in the cosmic landscape? Some physicists argue for the Anthropic Principle, the idea that we observe this particular universe because it's the only kind where observers like us could exist. In other words, the reason we find ourselves in a universe with 3 stable dimensions and just the right amount of dark energy isn't because it's the only option, but because it's the only option where someone could be around to notice. It's like a puddle marveling at how perfectly its hole fits its shape, not realizing there are countless other holes out there, most of them empty, yet others push back, insisting there must be a deeper mechanism at work. Could some undiscovered law of physics steer universes toward life-friendly conditions, like a river carving a path through rock? Or are we missing an even bigger picture, one where universes reproduce through black holes or quantum fluctuations, creating an evolutionary pressure toward complexity? The debate cuts to the heart of science itself. Is our universe the product of blind chance, or is there a hidden logic woven into the fabric of reality? The wildest implication: if the cosmic landscape is real, then every time a quantum fluctuation or a black hole collapse spawns a new universe, it might emerge with totally different dimensions and physical laws. Somewhere out there, a universe could exist where time runs backward or where gravity repels instead of attracts. And if string theory's math holds, these alternate realities aren't science fiction, they are inevitable. The challenge is that we're stuck in our own valley with no way to climb the ridges and peek into the next one. Still, there are glimmers of hope. If our universe bubbled off from a parent universe in the landscape, it might carry faint scars from that birth, patterns in the cosmic microwave background, or anomalies in the distribution of galaxies. Telescopes like the James Webb are already scanning the skies for these cosmic fingerprints. Others are probing the quantum foam of empty space, hunting for signs of other universes brushing against ours in higher dimensions, like soap bubbles touching in a sink. What makes this theory so thrilling isn't just its scale, it's the way it turns the search for meaning into a scientific question. For centuries, we've wondered why the universe seems tailor-made for life. Now we're staring at a possible answer. It isn't. We're just the lucky ones who ended up in the neighborhood where the numbers worked out. And if that's true, the cosmic landscape isn't just a theory, it's a mirror, forcing us to confront our place in a reality far stranger and far grander than we ever imagined. Imagine a universe where every event inside a vast, warped space, every collision of particles, every dance of forces is perfectly mirrored by interactions playing out on its distant, lower dimensional boundary. This isn't science fiction. It's the astonishing promise of the AD/CFT Correspondence, a theory so profound, it challenges our very understanding of where reality begins and ends. At its heart lies a revelation. A universe with gravity in 5 dimensions could be mathematically equivalent to a 4-dimensional world without gravity at all. It's as if the cosmos is performing an elaborate magic trick, convincing us that depth and dimension are illusions, that the universe's true workings might be written on a surface we've yet to fully comprehend. The roots of this idea trace back to the late 1990s, when physicist Juan Maldacena uncovered a startling connection between 2 seemingly unrelated branches of physics, string theory and quantum field theory. Anti-de Sitter space, or AD/S, is a peculiar kind of universe where space-time curves inward like a hyperboloid, creating a boundary where light can reach infinity in finite time. On this boundary, particles interact according to conformal field theory, or CFT, a framework that describes quantum phenomena without gravity. Maldacena's breakthrough was showing that these 2 descriptions aren't just similar, they're dual. Every fluctuation in the higher dimensional AD/S space has a precise counterpart in the lower dimensional CFT, like a hologram projecting a 3-dimensional image from a 2-dimensional film. To grasp how radical this is, picture a fish tank with a security camera trained on it. The tank's interior, the swirling water, the darting fish, represents the higher dimensional AD/S space with gravity bending its dynamics. The camera's 2-dimensional feed, displayed on a monitor, is the CFT boundary, encoding all the same information without any explicit gravity. The AD/S/CFT correspondence claims that these are not just 2 views of the same system, they're fundamentally the same reality, described in different languages. A storm in the tank might correspond to pixelated static on the screen, but both tell the same story. Why does this matter? For decades, physicists have struggled to reconcile quantum mechanics, which governs the very small, with general relativity, which describes gravity's grip on the cosmos. The AD-S/CFT duality offers a tantalizing path forward. By translating gravitational problems into quantum ones, we might finally crack the code of quantum gravity. Think of it like a Rosetta Stone for physics, allowing us to translate the mysteries of black holes or the early universe into a language we already understand. Some researchers are already using this approach to explore the infamous information paradox, the question of whether data swallowed by a black hole is truly lost. If AD-S/CFT holds, the answer might lie not in the black hole's depths, but on its event horizon, where quantum interactions preserve information like a cosmic backup drive. Of course, the theory isn't without its skeptics. Our universe doesn't resemble anti-de Sitter space, it's closer to a de Sitter space, which expands exponentially due to dark energy. Critics argue that AD-S/CFT might be a mathematical curiosity with limited real-world applicability. Yet even if true, the duality's elegance is undeniable. It suggests that the universe operates on layers of meaning, with higher dimensional events encoded on lower dimensional surfaces in ways we're only beginning to decipher. Some even speculate that our own three-dimensional reality could be the projection of a two-dimensional boundary at the edge of space-time, a notion that would make Plato's cave allegory look quaint by comparison. The most exciting frontier lies in testing these ideas. While we can't create anti-de Sitter spaces in a lab, we can simulate their quantum counterparts using ultra-cold atoms or entangled qubits. These experiments might reveal whether the AD-S/CFT correspondence is a universal principle or a beautiful but niche insight. Either way, the theory has already reshaped how we think about dimensions, gravity, and the very fabric of reality. It whispers a provocative possibility that the universe's most profound secrets aren't hidden in the depths of space, but written quite literally on its walls. And if we learn to read them, we might finally understand the cosmic script that binds all dimensions together. The universe might be playing an elaborate game of origami with hidden dimensions, folding them into shapes so intricate they dictate the very fabric of reality. At the heart of this cosmic origami are Calabi-Yau Manifolds' six-dimensional geometries so complex, even their shadows in 3 dimensions resemble fantastical sculptures, twisting and looping in ways that defy ordinary intuition. These aren't just mathematical curiosities. They could be the reason an electron has its specific mass, why gravity is absurdly weak compared to other forces, and even why the universe has precisely 3 spatial dimensions we can perceive. Imagine a cosmic lock, and these shapes are the key, except the lock is everything that exists, and the key is woven from dimensions we can't see. Take a humble guitar string as an analogy. Pluck it, and the vibrations produce musical notes, each pitch determined by the string's length and tension. Now replace the string with a Calabi-Yau manifold, and the notes become the fundamental particles of nature. The way these shapes curl and knot in higher dimensions influences how strings vibrate within them, which in turn determines whether a particle becomes a quark, a photon, or something else entirely. It's as if the universe has a hidden tuning mechanism, and the geometry of these shapes is the dial. Even the number of holes and handles in a Calabi-Yau, its topological fingerprint, could explain why we observe exactly 3 generations of matter particles: electrons, muons, and taus, or up quarks, charm quarks, and top quarks. The elegance is staggering. The diversity of everything in existence might boil down to the folds of unseen dimensions. But how do you study something you can't observe? Here's where theoretical physics meets sheer creativity. Researchers use advanced algebraic geometry, a branch of math so abstract it's often described as doing equations in invisible ink, to explore these shapes. Supercomputers simulate their properties, revealing how particles might behave if they're trapped in these higher dimensional landscapes. Some models suggest that the reason gravity seems feeble in our world is because it's diluted, spreading out into the labyrinthine folds of Calabi-Yau spaces. Meanwhile, other forces like electromagnetism remain tightly confined to our three-dimensional slice of reality. It's like comparing a whisper in a cathedral to a shout in a closet. The same energy, but perceived vastly differently depending on the space it fills. The stakes couldn't be higher. If we could map the exact shape of these hidden dimensions, we might finally crack the code of string theory, unifying all forces and particles under a single framework. Experiments like the Large Hadron Collider are indirectly probing these ideas, searching for particles that could only exist if extra dimensions are curled in specific ways. Others are scouring the cosmos for anomalies in the way light travels across billions of years, hunting for distortions that might betray the presence of these geometric fingerprints. Even quantum computers are being enlisted to simulate Calabi-Yau dynamics, offering glimpses into realms no telescope will ever reach. Yet the most poetic implication isn't just scientific, it's philosophical. If Calabi-Yau shapes are real, then the universe isn't just governed by laws but by geometry. The reason you're made of carbon and not antimatter, the reason stars shine and black holes devour, might ultimately trace back to the silent, unseen folds of dimensions we'll never walk through. It's a humbling thought. The answers to existence's biggest questions might not be written in equations alone, but in the hidden contours of a geometry beyond our senses. And somewhere in the intricate dance of these shapes, the universe might be hiding its next great revelation. Deep beneath the French-Swiss border, where protons race around a 17-mile ring at nearly the speed of light, scientists might be on the verge of uncovering something extraordinary, not just new particles, but entire dimensions hidden from view. The Large Hadron Collider, the most powerful particle smasher ever built, isn't just probing the building blocks of matter, it's hunting for whispers from realms beyond our own. Here's how it works. When particles collide at unimaginable energies, they could briefly unleash graviton's hypothetical particles that carry gravity's force. But unlike photons or electrons, these gravitons wouldn't stick around. If extra dimensions exist, they might vanish into them like marbles rolling off a table, leaving behind a trail of missing energy that detectors can't fully account for. It's the cosmic equivalent of hearing footsteps in an empty room. You can't see what made the sound, but you know something's there. What makes this search so electrifying is the sheer audacity of the method. We're not building telescopes to peer into distant galaxies or launching probes to explore other planets. Instead, we're recreating the conditions of the universe's infancy, fractions of a second after the Big Bang, hoping to catch a flicker of something that shouldn't, or rather, couldn't exist in a three-dimensional world. Imagine throwing two pebbles into a pond and watching the ripples collide. Normally, you'd expect splashes and waves, but if some of that energy simply disappeared without a trace, you'd suspect there's a hidden drain beneath the surface. That's exactly what physicists are looking for in the debris of particle collisions. Energy that vanishes without explanation, a smoking gun for dimensions beyond our perception. But why gravitons? In theories like string theory, gravity's puzzling weakness compared to other forces could be because it's not confined to our three-dimensional brain of existence. While electromagnetism and nuclear forces are trapped here, gravity might be free to seep into higher dimensions, diluting its strength in our world. Gravitons escaping into these dimensions would leave gaps in collision data, like a puzzle with missing pieces that point to a larger picture. Already, the LHC has scoured mountains of data for these anomalies, ruling out certain energy ranges where extra dimensions could have been hiding. Yet the search is far from over. With upgrades pushing the collider to even higher energies, the next few years could deliver the breakthrough we've been waiting for, or force us to rethink the rules of the game entirely. Of course, not everyone is convinced. Skeptics argue that missing energy could stem from mundane sources, detector glitches, incomplete models, or particles we already know behaving in unexpected ways. Others point out that if extra dimensions are curled up smaller than a quadrillionth of an atom, even the LHC's colossal power might not be enough to reveal them. But that's the thrill of frontier science. The most revolutionary discoveries often lie just beyond the edge of what we deem possible. The implications stretch far beyond particle physics. If colliders uncover evidence of higher dimensions, it wouldn't just validate decades of theoretical work, it would fundamentally alter our understanding of reality. Suddenly, concepts like branes, string vibrations, and even parallel universes would shift from speculative math to testable science. We might finally grasp why gravity is the odd one out among forces, or why the universe seems so finely tuned for life. And who knows, the next big discovery might not be a particle at all, but a fingerprint, a subtle, higher dimensional signature waiting in the data, ready to rewrite the story of everything. So while the LHC's protons keep circling and detectors sift through the aftermath of countless collisions, one thing is certain: the universe has never been content to play by the rules we've given it. And if hidden dimensions are real, the greatest revelation might not be that they exist, but that they've been there all along, just out of reach, waiting for us to look in the right place. Dark energy isn't just a placeholder for our cosmic ignorance. It might be the first tangible clue that the universe is hiding dimensions beyond our perception. Imagine blowing up a balloon with tiny ants crawling on its surface. As the balloon expands, the ants notice their world stretching, but they have no way to detect the breath filling it from a higher dimension. In the same way, dark energy's relentless push, accelerating galaxies apart, could be the side effect of forces acting in directions we can't point to. The math behind this is as elegant as it is radical. If extra dimensions exist, their energy might subtly warp our three-dimensional space, creating the illusion of an unknown force we've labeled dark energy. Consider the vacuum of space. Far from empty, it's a seething quantum foam where particles flicker in and out of existence. In higher dimensional theories, this vacuum could have layers, like an ocean with unseen currents beneath its surface. Dark energy might be the pressure difference between our brane and adjacent ones, a cosmic equilibrium playing out in dimensions we can't access. It's like feeling a breeze through a window without ever seeing the wind. Some models even suggest that dark energy's puzzling consistency, its uniform density across the cosmos, makes perfect sense if it's not a local phenomenon but a global feature of higher dimensional geometry. The stakes are astronomical. If dark energy truly stems from extra dimensions, it would solve one of cosmology's biggest headaches: why its measured value is so bafflingly small compared to theoretical predictions. In a three-dimensional world, quantum calculations suggest the vacuum energy should be 120 orders of magnitude stronger than what we observe. But if that energy is diluted across higher dimensions, like ink spreading through folded cloth, the mismatch vanishes. Suddenly, dark energy's feeble strength isn't a paradox, it's a fingerprint of the universe's hidden architecture. How could we test such an extraordinary claim? The answer lies in the universe's oldest light, the cosmic microwave background. tiny irregularities in this afterglow might encode traces of higher dimensional gravity's influence. Next-generation telescopes like the European Space Agency's Euclid mission are mapping these patterns with unprecedented precision, hunting for anomalies that could betray dark energy's dimensional origins. Others are simulating colliding branes in supercomputers, predicting how such events would ripple through space-time. If these ripples match observed large-scale structures in the cosmos, it could be the smoking gun we've been searching for. Yet skeptics urge caution. Dark energy could still be an intrinsic property of space itself, unrelated to extra dimensions. Alternative theories like quintessence, a dynamic energy field that changes over time, remain contenders. But that's the beauty of science at the frontier. Every mystery is an invitation to dig deeper. Whether dark energy unlocks the secrets of higher dimensions or leads us down another path entirely, one thing is clear: the universe is far stranger than we ever imagined. And the answers we're seeking might not lie in distant galaxies, but in the invisible folds of reality itself, waiting for us to peel back the next layer. The Fermi Paradox has haunted scientists for decades. If the universe is so vast and old, why does it seem so empty? Where are the alien megastructures, the interstellar signals, the undeniable proof that we're not alone? One unsettling possibility cuts deeper than the rest. What if advanced civilizations aren't ignoring us, but exist right alongside us, hidden in dimensions we can't perceive? Imagine ants crawling across the forest floor, unaware of the hikers striding above them. To those hikers, the ants are trivial, almost invisible. Now picture humanity as the ants, and the hikers as beings who have mastered higher dimensional physics, able to step outside our three-dimensional plane at will, leaving no trace we'd ever recognize. This isn't just speculative fiction. If extra dimensions are real and if a civilization learned to navigate them, their technology would defy our understanding entirely. Communication might happen through quantum entanglements in higher dimensional space, bypassing light-speed delays. Their structures could be folded into geometries our eyes can't resolve, like a two-dimensional creature failing to grasp the depth of a cube. Even their planetary systems might orbit stars anchored in branes parallel to ours, forever out of reach. The silence of the cosmos wouldn't stem from absence, but from a fundamental mismatch in how we perceive reality. Consider the implications. A civilization harnessing extra dimensions could colonize galaxies without crossing the space between them, slipping through wormholes or warped geometries like shortcuts on a crumpled map. They might harvest energy from the fabric of space-time itself, leaving no waste heat for our telescopes to detect. And if their very biology evolved to interface with higher dimensions, their existence could be as incomprehensible to us as quantum physics is to a goldfish. The great filter, the hypothetical barrier preventing life from reaching interstellar scales, might not be extinction, but transcendence into realms we're blind to. Some physicists take this further, suggesting that advanced beings might deliberately obscure their presence. Just as we protect uncontacted tribes from unintended harm, a higher dimensional civilization could observe us from a respectful remove, their influence so subtle it's indistinguishable from natural phenomena. Dark matter's gravitational tug, perhaps the residue of their infrastructure, unexplained cosmic rays, artifacts of experiments conducted in dimensions we can't access. Even UFO sightings, often dismissed as noise, could be fleeting glitches, like shadows cast by objects passing through our brain from elsewhere. Yet the most humbling thought isn't that we're being ignored, it's that we might lack the tools to even recognize the signals. Imagine trying to explain the internet to someone who's never seen electricity. If higher dimensional civilizations communicate via gravity waves modulated in 11 dimensions, or through quantum fluctuations in hidden geometries, our radio telescopes would be as useless as smoke signals in a thunderstorm. The paradox dissolves into a question of perception. We're not alone in a silent universe, but adrift in a symphony where we're deaf to most of the notes. So how do we test such a radical idea? Breakthroughs might come from unexpected places. Gravitational wave astronomy could uncover anomalies patterns that suggest artificial manipulation of space-time. Quantum computers might one day simulate higher dimensional physics, revealing protocols for dimensional communication. Or perhaps, as we unravel the mysteries of string theory and brains, we'll stumble upon signatures of engineering far beyond our own. Until then, the Fermi Paradox stands as both a riddle and an invitation to look beyond the dimensions we know and consider that the cosmos might be far more crowded and far stranger than it appears. What if everything you've ever felt, seen, or experienced, every star in the sky, every thought in your mind, is nothing more than data processed in a universe-sized computer? The simulation argument takes the idea of hidden dimensions and flips it on its head, suggesting they might not just be unseen layers of reality, but the very framework of a cosmic simulation. Think of it like this: when you play a video game, the characters don't know they're bound by the limits of your console's hardware. Their world exists only as far as the code allows. Now imagine our universe operates the same way, with higher dimensions acting as the unseen processors rendering our existence in real time. This isn't just philosophical musing, it's a hypothesis some scientists treat seriously. If extra dimensions exist, they could provide the computational space needed to run a simulation as complex as our universe. Just as a 3D game requires a computer with memory and processing power beyond the game's two-dimensional screen, our 3D reality might rely on higher dimensional machinery to function. The laws of physics, merely the algorithms governing the simulation. Quantum indeterminacy, the strange way particles behave until observed, could be the program optimizing resources, only rendering details when needed. Even the speed of light might not be a fundamental limit, but a built-in buffer to prevent the system from crashing. But how could we ever test such a mind-bending idea? Some researchers propose looking for glitches, in reality tiny inconsistencies in the fabric of physics that hint at underlying code. For example, if energy or information ever appears to vanish without cause, it might be evidence of a computational shortcut. Others suggest that the precise mathematical structure of the universe, with its eerily clean constants like the fine structure ratio, resembles the elegant code of an engineered system. There's even a fringe effort to hack the simulation by exploiting potential loopholes in quantum mechanics, like creating states so complex they'd overload the system's processing power. The implications are staggering. If we're living in a simulation, the creators, whether they're advanced civilizations or future humans, could be observing us like players in a godlike game. Dark matter and dark energy might not be physical substances, but background processes keeping the simulation stable. Religious experiences or déjà vu could be artifacts of the program briefly interacting with our consciousness. And if the simulation ever shuts down, well, that might be the ultimate cosmic apocalypse, not with a bang, but with a power down. Yet the simulation argument isn't without its critics. Many physicists argue that it's unfalsifiable, a fun thought experiment, but ultimately untestable. Others point out that simulating an entire universe would require impossible amounts of energy unless the simulators exist in a reality with entirely different physical laws. And then there's the existential question. If we're just lines of code, does meaning itself dissolve? Not necessarily. even in a simulation, our emotions, discoveries, and connections could be just as real to us as they are now. The universe, simulated or not, is the only one we've got. Whether the simulation hypothesis holds water or not, it forces us to confront a profound possibility. Reality might not just have hidden dimensions, it might have hidden architects. And if that's true, the greatest scientific discovery wouldn't be finding the source code of the cosmos, but realizing we've been living inside it all along. Consciousness might be the most intimate mystery we'll ever confront, the vivid, undeniable experience of being you right here, right now. But what if that sense of self isn't confined to the 3 dimensions we know? What if the mind isn't just a product of neurons firing in your brain, but a multidimensional phenomenon tapping into realms beyond space and time? It's a theory that straddles the line between physics and philosophy, suggesting that intuition, déjà vu, or even that eerie feeling of knowing something before it happens could be glimpses into higher dimensional interactions. Think of it like this: your brain could be a radio tuned to the familiar frequencies of 3-dimensional reality, but occasionally the signal drifts, picking up whispers from stations broadcasting in directions you can't point to. That sudden flash of insight, the uncanny sense of familiarity in a place you've never been, these might not be glitches, but moments when your consciousness briefly brushes against dimensions where time isn't linear, or where information flows in ways our physics can't yet describe. Even memory, that fragile thread tying us to our past, might not be stored in synapses alone, but in folds of higher dimensional space, like pages in a book we can't fully open. The math behind this is as speculative as it is fascinating. In certain brane-world models, the brain's electromagnetic fields could interact with hidden dimensions, resonating like a tuning fork struck in an echo chamber we can't see. Some theories propose that quantum processes in microtubules, tiny structures inside neurons, might act as gateways, entangling with higher dimensional geometries to produce subjective experience. It's a modern twist on Descartes' old dilemma. Instead of a ghost in the machine, we might be dealing with a dimensionally extended ghost, its roots tangled in the fabric of reality itself. Skeptics, of course, dismiss this as wishful thinking, a desperate attempt to pin consciousness on something grander than biology. After all, if higher dimensions exist, why would evolution bother with something as messy as a meat-based brain? But proponents counter that evolution works with what's available. If consciousness does tap into extra dimensions, even weakly, it could explain why humans developed such complex cognition so quickly, like a species stumbling upon a hidden wellspring of processing power. The implications spiral outward. If consciousness connects to higher dimensions, near-death experiences or psychedelic visions might not be mere hallucinations, but temporary expansions of perception, like a 2-dimensional creature suddenly glimpsing depth. Meditation traditions that speak of transcending time and space could be describing literal shifts in dimensional awareness. Even artificial intelligence might hit a ceiling unless we account for these unseen layers, building machines that don't just compute, but perceive in dimensions beyond our own. Of course, testing this borders on the impossible. How do you design an experiment for subjective experience? Yet some researchers are trying. Quantum consciousness experiments probe whether the brain exhibits non-local effects, while advanced EEG studies hunt for neural patterns that defy 3-dimensional cause and effect. Others are simulating higher dimensional networks to see if they spontaneously produce consciousness-like properties. Whether this theory holds water or evaporates under scrutiny, it forces us to confront a humbling possibility. The mind might not be a prisoner of the skull, but a wanderer in dimensions we're only beginning to imagine. And if that's true, the greatest frontier of exploration isn't outer space, it's the hidden geometry of thought itself. time crystals sound like something ripped from the pages of a sci-fi novel. Structures that don't just exist in space, but pulse and repeat in time itself, like a snowflake that perpetually melts and refreezes without losing energy. Normally, the idea of perpetual motion defies the laws of physics, but in the bizarre quantum realm, time crystals dance to a different tune. They're not breaking the rules, they're bending them, achieving a form of motion without energy input by leveraging the quantum equivalent of a loophole. Now, imagine these already strange objects not confined to our three-dimensional world, but thriving in higher dimensional frameworks where time itself might have hidden layers. The implications aren't just revolutionary, they're paradigm-shattering. In our familiar universe, crystals like diamonds or salt are prized for their repeating spatial patterns, their atoms arranged in perfect lattices. Time crystals flip this script. Instead of repeating in space, their structure oscillates in time, returning to their original configuration at regular intervals without any external push. It's as if you tapped a piano key once and the note kept playing forever, sustained by some unseen cosmic rhythm. This isn't magic, it's a delicate quantum phenomenon, first theorized in 2012 and later observed in labs using chains of ions or diamond defects. But here's the twist. In higher dimensions, time crystals might not be rare curiosities. They could be as natural as snowflakes in a blizzard. Why would extra dimensions make time crystals more stable or abundant? Think of it like weaving a tapestry. In 3 dimensions, the threads of quantum states are fragile, easily unraveled by decoherence, the enemy of all quantum systems. But in higher dimensions, those threads could have more anchors, more ways to intertwine and reinforce each other. Time crystals might find a kind of dimensional scaffolding, allowing their rhythmic patterns to persist far longer than they ever could in our limited spatial framework. Some string theory models even suggest that higher dimensional time crystals could act as cosmic clocks, their oscillations syncing with the vibrations of hidden dimensions, like pendulums swinging in unison across unseen realms. The real-world applications are just as mind-bending. Quantum computers, which today are notoriously finicky, could leverage time crystals to stabilize qubits, the building blocks of quantum information. Imagine a qubit that doesn't just hold its state for microseconds, but for hours or days, thanks to higher dimensional time crystal structures embedded in its design. It's like upgrading from a sandcastle to a diamond fortress. Suddenly, quantum calculations that were once impossible due to noise and decay could run flawlessly. Labs are already toying with this idea, using time crystals to prototype error-resistant quantum memory. If higher dimensions are indeed the key, we might be on the verge of a computing revolution, one where the chips themselves tap into physics beyond our perception. But the most tantalizing possibility isn't technological, it's existential. If time crystals exist more naturally in higher dimensions, their behavior could serve as a cosmic breadcrumb trail, leading us to evidence of those dimensions themselves. Experiments might one day detect anomalies in time crystal oscillations patterns that only make sense if extra dimensions are subtly influencing their rhythm. It'd be like listening to a song and realizing the echo isn't just reverb, but a duet with a singer you can't see. Of course, skeptics argue that time crystals are still too poorly understood to make such grand claims. Yet that's the thrill of frontier science. The wildest ideas often illuminate paths no one thought to walk. Whether time crystals become the linchpin of quantum technology or simply another piece of the multidimensional puzzle, one thing is certain: they're proof that the universe still has tricks up its sleeve, and the most astonishing discoveries might not lie in the distant cosmos, but in the hidden dimensions of time itself. The Big Bang has always been framed as the ultimate beginning, a fiery birth from nothingness. But what if that explosive moment wasn't creation at all, but a metamorphosis? Imagine the universe as a piece of ice forming in supercooled water. One instant, it's liquid and free. The next, it's locked into rigid structure. That's the essence of the dimensional transition theory, a radical reimagining where our cosmos didn't emerge from nothing, but froze into its current form, trading higher dimensional fluidity for the three spatial dimensions we know today. Picture standing in a pitch-black room as someone slowly turns up a dimmer switch. At first, shadows and shapes blur together, no clear boundaries, no up or down. Then, as the light brightens, the world snaps into focus. Walls, floor, ceiling. The dimensional transition theory suggests the Big Bang was that moment of cosmic clarity. Before it, reality might have existed in a state of dimensional ambiguity where time and space were interchangeable. Directions had no fixed meaning, and the very concept of before was meaningless. Then, as the universe cooled, dimensions crystallized like ice forming in chaotic water, three spatial dimensions expanding, while others contracted or hid themselves at scales too small to perceive. This isn't just poetic speculation. The math behind this idea draws from string theory and loop quantum gravity, where the early universe's extreme energy could have allowed all dimensions to exist equally. As temperatures dropped, symmetries broke, like a molten metal solidifying into a crystal lattice, locking us into the three-dimensional framework we experience. Time's arrow, always puzzling in physics, might simply be the direction along which this crystallization unfolded. What we perceive as the Big Bang's explosive expansion could be the aftershock of dimensional settling, like wrinkles smoothing from a stretched sheet. The implications rewrite cosmology's biggest questions. If the Big Bang was a phase transition, there was no true nothingness before it. Just a state of reality so alien, our language lacks the words to describe it. The infamous singularity at time zero, perhaps not an infinite density point, but a dimensional boundary, like the surface of a bubble where inside and outside obeyed different rules. Even dark energy's mysterious push could be a relic of this transition, the universe's latent memory of higher dimensional freedom, subtly resisting its three-dimensional confines. How do we test such a mind-bending idea? The cosmic microwave background, the afterglow of the Big Bang, might hold clues. Certain anomalous patterns in its temperature fluctuations could reflect pre-transition turbulence, like swirls in water moments before freezing. Particle colliders, too, might glimpse hints. If extra dimensions exist, smashing protons at extreme energies could briefly recreate the primordial, dimensionally fluid state, producing exotic particles that wink in and out of our observable reality. Yet the most profound consequence isn't scientific, it's philosophical. If our universe is just one possible crystallization from a vast dimensional landscape, others might have frozen differently. Some could have four spatial dimensions with physics we can't begin to fathom. Others might lack stable dimensions altogether, their laws in constant flux. We're left with a humbling thought. The Big Bang wasn't the beginning of everything, but the moment our particular slice of reality took shape, a single frame in a far grander, multidimensional film still rolling. Whether this theory stands or falls, it challenges us to rethink the most foundational story we tell about existence. The universe isn't just expanding, it might still be settling, its hidden dimensions whispering of possibilities beyond our grasp. And if we listen closely, the echoes of that transition might still be ringing in the fabric of space-time, waiting to be decoded. Neutrinos are the universe's ultimate escape artists, particles so ghostly, they can pass through light years of lead without a single collision. Billions stream through your body every second, leaving no trace, as if reality itself is little more than a faint mist to them. but what if their elusiveness isn't just a quirk of their nature? What if neutrinos are slipping through dimensions we can't see, vanishing and reappearing like cosmic magicians exploiting hidden trapdoors in space-time? The mystery begins with their vanishing act. Neutrinos come in three known flavors: electron, muon, and tau, and they constantly oscillate between these states as they travel. One moment, a detector catches an electron neutrino. The next, it's gone, only to reappear later as a tau neutrino. This shape-shifting behavior was first observed in experiments where neutrinos seemed to disappear en route from their source to the detector. The math explained the oscillations, but the sheer strangeness of it all left physicists wondering, could there be more to the story? Hidden dimensions offer a tantalizing twist. If neutrinos occasionally step out of our three-dimensional brane into higher dimensional space, even momentarily, it could explain why they seem to flicker in and out of detection. Imagine a mouse running through a maze with secret tunnels. Sometimes it's on the main path, sometimes it's not, and observers can't see where it went. Neutrinos might be doing the same, their oscillations not just between flavors, but between dimensions. This isn't just wild speculation. Certain string theory models predict that neutrinos could couple to extra dimensions more strongly than other particles, making them unique probes into the unseen architecture of reality. If true, every neutrino detection, or lack thereof, could be a tiny window into higher dimensional physics. Experiments like IceCube, buried deep in Antarctic ice, and Super Kamiok, and a colossal tank of ultra-pure water in Japan, are already hunting for anomalies in neutrino behavior that might betray these dimensional detours. The stakes are higher than just solving a particle physics puzzle. If neutrinos are indeed traversing extra dimensions, they could be carrying back whispers from realms beyond our perception. Tiny discrepancies in their energy or oscillation patterns might encode the geometry of hidden dimensions like a ship's wake, revealing the shape of an invisible current. Some theorists even suggest that sterile neutrinos, hypothetical, even more elusive cousins of the known flavors, could be entirely confined to higher dimensions, only interacting with our world gravitationally. Yet skeptics argue that Occam's razor should apply. Neutrino oscillations might just be a quirky property of quantum mechanics, no extra dimensions required. But that's the thrill of science at the edge. Sometimes the simplest explanation isn't the right one. Whether neutrinos are dimensional travelers or not, their ethereal nature ensures they'll keep haunting the frontiers of physics, teasing us with the possibility that the answers we seek aren't just hidden in plain sight, but in dimensions just beyond our grasp. Quantum mechanics paints a picture of empty space that's anything but empty, a seething, bubbling foam where particles flicker in and out of existence so fast they barely leave a trace. According to the math, this quantum froth should pack an unimaginable punch, infusing every cubic centimeter of vacuum with enough energy to rip the universe apart. Yet when we measure it, the vacuum's energy is almost laughably small, like expecting a tsunami and finding barely a ripple. This glaring mismatch, known as the vacuum catastrophe, isn't just a minor hiccup in physics. It's a full-blown crisis, suggesting we're missing something fundamental about the fabric of reality. Hidden dimensions might hold the key to this cosmic sleight of hand, acting as unseen valves that drain away the vacuum's excess energy before it can overwhelm our universe. Imagine blowing up a balloon inside a larger, invisible box. As the balloon expands, the box's walls absorb the pressure, keeping the balloon stable. Now replace the balloon with our three-dimensional universe and the box with higher dimensional space. The vacuum's staggering theoretical energy could be dissipating into these extra dimensions, canceling itself out like sound waves perfectly timed to silence each other. String theory offers a tantalizing mechanism for this. Calabi-Yau Manifolds, those intricate six-dimensional shapes, might not just dictate particle properties, they could also act as cosmic sponges, soaking up vacuum energy through their complex geometry. It's as if the universe has built-in shock absorbers, hiding in dimensions we can't perceive. The implications are staggering. If hidden dimensions are quietly neutralizing the vacuum's ferocity, they're not just solving a theoretical embarrassment, they're preventing reality from self-destructing. Without this delicate balancing act, dark energy's gentle nudge would be a crushing blow, flinging galaxies apart before stars could even form. Some models even suggest that the vacuum's observed energy isn't a constant, but the residual hum of higher dimensional dynamics, like the faint vibration of a tuning fork struck long ago. Future experiments could look for subtle variations in this energy, hunting for patterns that betray the presence of unseen dimensions. Yet skeptics argue this might be a band-aid on a deeper wound. Why should extra dimensions fine-tune the vacuum so precisely? An alternative view flips the script. Perhaps the vacuum's energy is small because it's not a property of space at all, but a kind of cosmic background noise left over from dimensional transitions in the early universe. Like ripples frozen in a pond, its value might be a historical accident, not a fundamental law. Others propose that our universe is a rare, low-energy bubble in a multiverse where most regions tear themselves apart, a sobering reminder of how precarious existence might be. The vacuum catastrophe forces us to confront an unsettling truth. The universe's apparent calm could be the result of forces playing out in realms we'll never see. Whether through hidden dimensions, multiversal luck, or physics we've yet to discover, the silence of empty space might be the most deafening clue that reality is far stranger than it appears. And if we're right, the answers we're seeking aren't just hidden in the voids between stars, they're woven into the very nothingness around us. Quantum gravity has been the holy grail of physics for over a century, the dream of uniting Einstein's cosmic-scale relativity with the frantic, probabilistic world of quantum mechanics. On the surface, these two frameworks couldn't be more different. General relativity paints gravity as the smooth curvature of space-time, a geometric dance where planets and stars move along invisible contours. Quantum mechanics, meanwhile, reduces reality to a chaotic subatomic carnival, where particles pop in and out of existence and certainty dissolves into probability clouds. The equations of one framework break down when applied to the other, like two brilliant musicians playing in different keys, but hidden dimensions might hold the sheet music to finally harmonize them. Picture trying to explain a rainbow to someone who's only ever seen shadows. You'd struggle to convey color without a shared language for wavelengths beyond their perception. That's the challenge physicists face when reconciling gravity and quantum mechanics, except the missing language might be higher dimensional geometry. String theory proposes that the fundamental building blocks of reality aren't point-like particles but tiny, vibrating strings. And just as a violin string produces different notes depending on how it vibrates, these cosmic strings manifest as different particles based on their oscillations. But here's the catch: their vibrations don't just play out in the 3 dimensions we know. They resonate through 6 or 7 additional dimensions, curled up into shapes so small they're invisible to our experiments. This is where the magic happens. In higher dimensional space, the contradictions between gravity and quantum mechanics start to soften. Gravity's weakness compared to other forces could stem from it, leaking into these extra dimensions, like water seeping through microscopic cracks. Quantum weirdness, like entanglement or superposition, might appear paradoxical in 3 dimensions but become elegant inevitabilities when viewed through a higher dimensional lens. Imagine 2 people arguing over whether a distant mountain is round or flat. Both are right, but only from their limited vantage points. Climb high enough and the truth reveals itself. The mountain is a cone, its full shape invisible from below. Similarly, the clash between relativity and quantum physics could vanish when we account for dimensions we've yet to perceive. Experiments are already hunting for traces of this unification. Gravitational wave detectors like LIGO might spot anomalies in ripples from colliding black holes, subtle distortions that betray the influence of extra dimensions. Particle colliders could create microscopic black holes, which would evaporate instantly in our three-dimensional world, but leave behind energy signatures hinting at higher dimensional escape routes. Even the cosmic microwave background, the afterglow of the Big Bang, might bear imprints of quantum gravitational effects from the universe's earliest moments, when all dimensions were unfurled and equal. Yet skeptics caution that string theory's elegance comes at a cost. Without direct experimental proof, the extra dimensions it relies on remain mathematical phantoms. Alternative approaches like loop quantum gravity attempt to reconcile relativity and quantum mechanics without invoking hidden dimensions, treating space-time as a network of interconnected loops. Others propose that gravity isn't fundamental at all, but an emergent phenomenon like temperature arising from the motion of atoms with quantum mechanics operating on a deeper, pre-geometric level. The beauty of this quest lies in its stakes. If higher dimensions do bridge quantum mechanics and gravity, it wouldn't just solve a theoretical puzzle, it would revolutionize our understanding of reality. Black holes, the birth of the universe, even the nature of time itself would need to be reinterpreted through a multidimensional lens. We might discover that the contradictions we've struggled with for decades weren't flaws in nature's design, but artifacts of our limited perspective. And that realization could be the key to unlocking physics' final frontier, a theory of everything written in the hidden dimensions we're only beginning to fathom. What if the universe is teeming with particles we can't fully detect, ghosts that flicker in and out of our reality like shadows passing through a veil? The phantom particle hypothesis dares to suggest just that. Entire families of particles might exist solely in higher dimensions, only occasionally brushing against our three-dimensional world. When they do, they leave behind bizarre anomalies, unexplained energy spikes in particle detectors, cosmic rays with no identifiable source, or even the gravitational tug we attribute to dark matter. These aren't just measurement errors or equipment glitches. They could be fleeting handshakes from dimensions beyond our own. Take dark matter as the prime suspect. For decades, scientists have searched for WIMP, weakly interacting massive particles, as the culprit behind the missing mass in galaxies. But what if dark matter isn't a particle in our universe at all? Imagine a higher dimensional realm where matter behaves just like ours, with stars, planets, and even civilizations, all invisible because their particles vibrate in directions we can't access. Occasionally, gravity from these phantom particles might leak into our dimension, like the faint rumble of footsteps from an upstairs neighbor. This wouldn't just explain dark matter's elusive nature, it would mean we're surrounded by an entire shadow universe, its presence only revealed through gravity's gentle pull. Particle colliders have already glimpsed tantalizing hints. At facilities like the Large Hadron Collider, detectors occasionally record bursts of energy that defy conventional physics, events where momentum seems to vanish into thin air. Normally, these are dismissed as background noise or instrument quirks, but if phantom particles are real, they could be darting into higher dimensions mid-collision, carrying energy with them like thieves slipping through a hidden door. It's as if you dropped a marble on the floor, only for it to vanish before hitting the ground, not because it's gone, but because it rolled into a dimension you can't see. Cosmic rays add another layer of intrigue. Some ultra-high-energy particles strike Earth's atmosphere with forces that shouldn't be possible if they've traveled across billions of light years. Conventional physics says they'd lose energy along the way, yet here they are, arriving with inexplicable punch. Phantom particles could solve this riddle. If these rays originate in higher dimensions, they might take shortcuts through warped space-time, avoiding the energy-draining drag of our universe entirely. Think of it like a hiker cutting through a mountain tunnel instead of climbing over the peak. The destination is the same, but the journey is far more efficient. The implications stretch beyond astrophysics. If phantom particles exist, they could rewrite the rules of quantum mechanics. Entanglement, the eerie link between particles across vast distances, might not be spooky action at a distance, but a mundane side effect of particles interacting in higher dimensions. Even the vacuum of space, supposedly empty, could be a bustling intersection where phantom particles constantly flit between realities, their presence only betrayed by the faintest gravitational ripples. Of course, skeptics argue that invoking extra dimensions to explain anomalies is a cop-out, a cosmic, we don't know, so let's blame the unseen. But history has a way of humbling our assumptions. Neutrinos were once dismissed as undetectable ghosts too, until we built the tools to catch them. The same could be true for phantom particles. Next-generation detectors, like the Deep Underground Neutrino Experiment or space-based gravitational wave observatories, might finally snag conclusive proof, an energy signature that defies three-dimensional logic, or a gravity anomaly that points unmistakably to matter bleeding in from elsewhere. Whether phantom particles are real or not, they force us to confront a profound possibility. The universe's greatest mysteries might not be missing pieces of the puzzle, but pieces from a different puzzle entirely, one playing out in dimensions we're only beginning to imagine. And if we're right, the answers we're seeking aren't lost. They're just hiding in plain sight, waiting for us to look in the right direction, or rather, in the right dimensions. Black holes have long been the ultimate cosmic conundrum, not just because of their crushing gravity, but because they seem to break one of the universe's most sacred rules: information can never be destroyed. Toss a book into a black hole, and according to classical physics, every word, every letter, every ink molecule is irretrievably lost, swallowed by the singularity. But quantum mechanics insists that information is indestructible, always preserved in some form. This clash isn't just academic. It strikes at the heart of whether reality is fundamentally predictable or chaotic. Hidden dimensions might hold the key to resolving this paradox, not by rewriting the laws of physics, but by revealing where the missing information has been hiding all along. Stephen Hawking's groundbreaking work showed that black holes aren't entirely black. They emit radiation, slowly evaporating over eons. But here's the catch: Hawking radiation appears random, like static on a radio, offering no clues about what fell in. If that's the full story, the information is truly gone, and quantum mechanics is broken. But what if the radiation isn't as random as it seems? Imagine a library where every burned book's ashes scatter in patterns that, if you knew how to read them, could perfectly reconstruct the original text. Hidden dimensions could provide the cipher to decode Hawking radiation's secrets. The math behind this is as elegant as it is mind-bending. In string theory, when a particle falls into a black hole, its information isn't crammed into the singularity. It's smeared across the event horizon like a hologram, encoded in tiny Planck-scale pixels. As the black hole emits radiation, that information could escape not just into our three-dimensional space, but into higher dimensional corridors, like a message written in invisible ink that only appears under the right light. The radiation might look random to us because we're missing the full dimensional context, like seeing only the shadows of a complex sculpture. Observational clues are already emerging. Gravitational wave detectors like LIGO have spotted subtle echoes in the signals from colliding black holes' ripples that don't match classical predictions. Some theorists argue these echoes could be evidence of information bouncing off higher dimensional structures near the event horizon, like sound waves in a resonant chamber. Others are analyzing the fine-grained details of Hawking radiation itself, searching for hidden correlations that might betray information's escape route. It's akin to listening to static and suddenly discerning the faint rhythm of a song buried beneath the noise. The implications go far beyond black holes. If information can traverse hidden dimensions, it might rewrite our understanding of entropy, time, and even the nature of causality itself. The universe could be far more interconnected than we realize, with data flowing through dimensions we can't perceive. It's a humbling thought. The answers to physics' greatest puzzles might not be lost after all. They've just been hiding in plain sight, waiting for us to look beyond the dimensions we know. The Boltzmann brane paradox is one of the most unsettling ideas in physics, not because it's complex, but because it's terrifyingly simple. Imagine a universe that lasts forever, where particles jostle at random for eternity. Given enough time, even the most improbable events become inevitable. At some point, a collection of atoms could spontaneously arrange itself into a fully conscious brain, complete with false memories of a life it never lived. Now ask yourself, how do you know you're not that brain, hallucinating this very moment into existence before dissolving back into chaos? This thought experiment, dreamed up by physicist Ludwig Boltzmann in the 19th century, was meant to highlight the strangeness of statistical mechanics. But in a multiverse teeming with hidden dimensions, the paradox takes on a new and even weirder life. If higher dimensional spaces exist, they could drastically increase the number of possible configurations for random fluctuations, making Boltzmann branes, or their multidimensional equivalents, far more likely than we'd ever guessed. Picture a deck of cards shuffled endlessly in 3 dimensions. The odds of getting a royal flush are slim, but if that deck spreads into extra dimensions, the number of possible hands explodes and suddenly, royal flushes appear all the time. The real kicker, hidden dimensions might also hand us a way to test whether we're the real deal or just cosmic background noise. If our universe is a stable, long-lived structure anchored in a higher dimensional landscape, the probability of being a Boltzmann brane plummets. After all, fleeting fluctuations don't build galaxies or encode the laws of physics into elegant equations. But if we're floating in a higher dimensional void, unmoored from any deeper structure, the math tilts the other way toward a universe where most conscious experiences are brief, illusory flickers. Some physicists argue that the very fact we observe a coherent, ordered cosmos is evidence against the Boltzmann nightmare. Complex structures like DNA, stars, and even YouTube videos are vanishingly unlikely to emerge from random noise. Others counter that in an infinite multiverse, even the most absurd scenarios must play out somewhere, including brains that hallucinate entire realities. Hidden dimensions add another layer. If they're compactified or warped in just the right way, they could act as cosmic stabilizers, preventing the chaos that would spawn Boltzmann branes en masse. The debate isn't just philosophical. Next-generation quantum sensors might detect subtle fluctuations in the vacuum of space, hints that our reality isn't as solid as it seems. If the fabric of space-time shows signs of instability, it could support the idea that we're riding a rare, ordered wave in a sea of chaos. Conversely, if experiments confirm that higher dimensions are structured and stable, the Boltzmann scenario fades into the realm of mathematical curiosity. What makes this paradox so haunting isn't the science, it's the existential vertigo it induces. Are we meaningful observers in a vast but rational cosmos, or just momentary glitches in the static of eternity? Hidden dimensions might not just hold the answer, they could redefine what it means to be real at all, and that's a question even a Boltzmann brain would find hard to shake. The cosmic microwave background is often called the universe's baby picture, a nearly uniform glow left over from the Big Bang, stretching across the sky with only tiny temperature variations. But in 2005, astronomers studying this ancient light stumbled onto something unsettling. The fluctuations weren't as random as they should have been. Instead, they seemed to align along a mysterious corridor in space, a so-called axis of evil, where temperatures dipped and rose in patterns that defied the cosmological principle, the idea that the universe should look the same in all directions. It was as if the cosmos had quietly drawn an arrow on itself, pointing toward something we couldn't see. At first, scientists assumed it was an error. Maybe satellite instruments had glitches or dust in our galaxy skewed the measurements. But as more precise data rolled in from missions like Planck, the anomaly refused to vanish. The axis wasn't just a fluke, it was a persistent whisper that the universe might have a preferred direction, a cosmic north that shouldn't exist in standard models. The implications were staggering. If space isn't perfectly uniform, if it has hidden asymmetries, what does that mean for our understanding of reality? One daring possibility is that this axis isn't just a quirk, it's a fingerprint of higher dimensions subtly warping the fabric of our universe from beyond our perception. Imagine blowing up a balloon with faint grid lines drawn on its surface. Inflate it evenly, and the grid stays uniform. But if an unseen hand presses against the balloon from the outside, from a dimension the balloon's two-dimensional residents can't perceive, the grid would stretch unevenly, creating patterns that seem inexplicable from within. The axis of evil could be doing the same to our three-dimensional universe. If higher dimensions exert even the slightest gravitational tug or curvature, they might leave imprints in the cosmic microwave background, like invisible fingers denting space-time itself. Some string theory models suggest these dimensions could be tilting our universe's expansion, creating directional biases that linger from the Big Bang. The most tantalizing clue lies in the axis's alignment. It eerily points toward the constellation Eridanus, but more strikingly, it lines up with the plane of our solar system, a coincidence so improbable, it's either a cosmic prank or a hint that our local structure is entangled with something deeper. Could our solar system's orientation be influenced by higher dimensional geometry, like a compass needle twitching toward a hidden magnet? Or is this axis a remnant of a primordial collision between our universe and another brane in a multidimensional landscape? Skeptics, of course, have other explanations. Some argue that the anomaly stems from incomplete data or unaccounted for foreground interference. Others propose less exotic fixes, like modified gravity or large-scale magnetic fields. But the higher dimensional hypothesis refuses to fade, partly because it offers something rare in cosmology, a testable prediction. If the axis is tied to hidden dimensions, future telescopes measuring the polarization of the cosmic microwave background might detect subtle swirls or distortions that betray their presence. Gravitational wave observatories could catch ripples propagating unevenly along the axis, like waves bending around an unseen obstacle. What makes the axis of evil so compelling isn't just the mystery, it's the audacity of the questions it forces us to ask. Are we living in a universe that's not just expanding but tilted? Is the cosmos subtly lopsided because of dimensions we've yet to map? Whether the answer lies in hidden realms or simpler astrophysics, one thing's clear: the universe is still capable of catching us off guard, revealing cracks in our understanding where the light of deeper truths might someday shine through. Imagine you're sitting perfectly still in a silent, empty room, a void where not even a single particle of dust floats. Now picture someone else hurtling through that same room at nearly the speed of light. To them, the room wouldn't feel empty at all. Instead, they'd be bathed in a glow of radiation, as if immersed in a warm thermal bath. This bizarre phenomenon is the Unravel effect, a quantum quirk where acceleration literally conjures particles out of nothingness. For decades, it's been a fascinating footnote in physics textbooks, a thought experiment so strange it seemed relegated to the realm of theory. But what if this effect isn't just a curiosity? What if, in a universe with hidden dimensions, the Unravel effect transforms into a cosmic metal detector, revealing the unseen geometry of reality itself? At its core, the Unravel effect is a dramatic demonstration of how observer-dependent reality can be. In quantum field theory, empty space isn't truly empty. It's a seething quantum foam where virtual particles flicker in and out of existence. Normally, these cancel each other out perfectly, leaving no trace. But an accelerating observer doesn't see this cancellation. Instead, their motion distorts the quantum fields around them, turning fleeting virtual particles into real, detectable radiation. It's as if the universe rewards extreme motion with a shower of particles like sparks flying from a grinding wheel. The faster you accelerate, the hotter this phantom glow becomes. For an astronaut punching the gas to near light speeds, the void would appear to ignite with heat. Now, introduce extra dimensions into the mix, and the Unravel effect becomes a potential Rosetta Stone for decoding the universe's hidden architecture. In higher dimensional theories, the way particles emerge from acceleration could shift dramatically. Think of it like this. If you're on a trampoline, jumping up and down creates predictable ripples in the fabric. But if that trampoline has unseen folds or extra layers beneath it, your jumps might produce strange echoes or unexpected vibrations. Similarly, in higher dimensions, the Unravel radiation might carry subtle fingerprints, anomalies in its temperature, polarization, or particle spectrum that betray the presence of directions we can't point to. Some models suggest that extra dimensions could dampen or amplify the effect, depending on how they're curled or warped. Others propose that certain particle signatures in Unravel radiation could only exist if gravity is leaking into additional dimensions. The real breakthrough would come if we could measure these deviations. Unfortunately, the Unravel effect is vanishingly weak under everyday conditions. An astronaut would need to accelerate at a quadrillion times Earth's gravity just to perceive a faint warmth. But physicists are nothing if not creative. One proposal involves using ultra-intense lasers to whip electrons around in circles so tight they'd experience Unravel-like effects in the lab. Another leverages the insane accelerations near black holes, where infalling matter might emit Unravel radiation distorted by higher dimensional gravity. Even quantum computers could play a role, simulating how Unravel particles behave in hypothetical multidimensional environments. The implications stretch far beyond detection. If the Unravel effect changes in higher dimensions, it could rewrite our understanding of quantum fields, gravity, and even the nature of reality itself. For instance, the Hawking radiation that black holes emit might share a deeper kinship with Unravel radiation than we realized, two sides of the same multidimensional coin. It could also hint at a profound truth, that particles themselves aren't fundamental but emergent phenomena, their existence dependent on the observer's motion through the hidden folds of space-time. What makes this 30-second theory so electrifying isn't just its potential to unveil extra dimensions. It's the way it blurs the line between nothing and something, between emptiness and existence. The universe, it seems, is far more malleable than we ever imagined, and the act of moving through it might be enough to stir the void into creation. And if we're right, the key to uncovering reality's deepest secrets might not lie in stillness, but in the wild, untamed thrill of acceleration. The Casimir effect is one of quantum physics' most peculiar party tricks. Place two metal plates unfathomably close together in a vacuum, and they'll snap together as if pulled by invisible strings. At first glance, it seems like magic, but the secret lies in the chaotic quantum foam beneath reality's surface. Empty space isn't empty at all. It's a seething ocean of virtual particles popping in and out of existence, their fleeting lives governed by Heisenberg's uncertainty principle. Normally, these particles cancel each other out perfectly, but squeeze them between plates narrower than a photon's wavelength, and something extraordinary happens. Only certain particle wavelengths can fit in that microscopic gap, while outside the plates, all wavelengths rage freely. The result, a pressure imbalance stronger on the outside, pushing the plates together with measurable force. It's like trying to clap underwater. The resistance isn't from the water itself, but from the way it changes the space between your hands. Now, imagine those plates aren't just passive players, but probes into the universe's hidden architecture. If extra dimensions exist curled up smaller than an atom, they could subtly alter the quantum foam's behavior between the plates. Picture blowing soap bubbles between two panes of glass. In 3 dimensions, the bubbles form predictable patterns, but introduce a hidden fourth spatial dimension, and those bubbles might stretch into shapes we can't perceive, distorting the foam's pressure in telltale ways. The Casimir force should follow precise mathematical predictions in a purely 3-dimensional world, but if higher dimensions are warping the quantum vacuum, microscopic deviations in that force could betray their presence. The hunt for these deviations is already underway. Nanotechnology has advanced to where we can position plates mere nanometers apart, distances so small they're measured in atoms. At these scales, even minuscule dimensional leakage would tweak the Casimir force's strength. Some experiments use not plates, but exquisitely crafted microscopic spheres, whose curvature amplifies any anomalies in the quantum vacuum's behavior. Others employ exotic materials like graphene, whose single atom thickness makes it hypersensitive to fluctuations. The challenge is separating dimensional whispers from background noise, like trying to hear a pin drop in a hurricane. But here's where it gets revolutionary. If extra dimensions are tweaking the Casimir effect, they might not just be passive hiding places, they could be dynamic participants in quantum mechanics. Certain string theory models suggest that what we call empty space is actually a higher dimensional membrane vibrating at frequencies we can't detect. The Casimir effect then becomes a cosmic guitar string, its tension revealing the shape of those hidden dimensions. Even dark energy's repulsive force might trace back to this, with higher dimensional geometries stretching the quantum foam like taffy, accelerating the universe's expansion. The implications are staggering. We might be on the verge of detecting extra dimensions not with billion-dollar particle colliders, but with tabletop experiments delicate enough to feel the universe's finest tremors. And if we succeed, it would mean that every time 2 microscopic plates click together in a lab, they're not just obeying quantum law, they're brushing against the fabric of reality's deepest layers. The answers we're seeking could be hiding in the quietest force we've ever measured, waiting for us to listen closely enough. The Pioneer Anomaly was one of those cosmic head-scratchers that lingered for decades, a tiny but persistent mystery that refused to go away. When NASA Pioneer 10 and 11 probes sailed through the outer solar system, scientists noticed something odd. Their trajectories were ever so slightly off, as if an invisible hand had gently tugged them backward. The deceleration was minuscule, less than a billionth of a meter per second squared, but it defied all conventional explanations: thermal radiation, instrument error, gravitational tugs from unknown objects, nothing quite fit. For years, this discrepancy haunted the edges of astrophysics, a whisper that maybe, just maybe, there was something fundamental we were missing. Enter the tantalizing possibility of hidden dimensions. If gravity isn't confined to our familiar three-dimensional space but leaks into higher dimensional realms, its effects could subtly warp the motion of objects in ways Newton and Einstein never predicted. Picture a ship sailing across the ocean, its path slightly altered by underwater currents it can't see. Pioneer's unexpected slowdown might have been a ripple from one of those unseen currents, a higher dimensional gravity, drag nudging the probes off course. The math behind this is as elegant as it is speculative. Certain brane-world models suggest that gravity's strength could vary at different scales, weakening or strengthening in ways that leave fingerprints on spacecraft trajectories. But here's the twist. In 2012, after painstaking analysis, researchers finally cracked the case. The anomaly wasn't a sign of new physics, just the gentle push of heat radiating unevenly from the probe's plutonium-powered generators. Case closed, right? Not so fast. While Pioneer's mystery was solved, the door it opened never fully shut. Other spacecraft, like the Galileo and Ulysses missions, showed similar quirks in their flight paths. And let's not forget the infamous flyby anomaly, where satellites gain or lose speed inexplicably during Earth gravity assists. Could these be cosmic breadcrumbs leading us toward higher dimensional gravity's subtle influence? The real lesson of the Pioneer anomaly isn't that we were wrong. It's that the universe loves to keep us on our toes. Even debunked mysteries can point toward deeper truths. Future missions, like the ultra-precise gravity probes being developed today, could scour these anomalies for fingerprints of extra dimensions. Imagine a spacecraft so sensitive, it detects gravitational tugs smaller than a butterfly's wingbeat. If hidden dimensions are out there, their whispers might finally be loud enough to hear. So while Pioneer's story ended with a thermal whimper, its legacy lives on as a reminder. Sometimes the smallest discrepancies hold the biggest clues. And in the hunt for dimensions beyond our perception, even the faintest anomalies deserve a second glance, because the universe's greatest secrets often hide in plain sight, masquerading as noise until someone dares to listen. The WOW signal remains one of the most tantalizing mysteries in astronomy, a burst of radio waves so powerful, it made an Ohio State University astronomer scrawl, "Wow," in red ink on the data printout. For 72 seconds in August 1977, a signal blared from the constellation Sagittarius, matching the exact frequency scientists predicted an extraterrestrial transmission would use. Then, just as suddenly, it vanished, never to be heard again. Decades of searching have turned up nothing, no repeat signal, no natural explanation that fully fits. But what if we've been looking in the wrong dimension? Hidden dimensions could rewrite this cosmic whodunit. Picture a radio left playing in a sealed room. To someone outside, the music might seem faint, distorted, almost ghostly, as the sound bleeds through walls and insulation. Now imagine that room is another universe, separated from ours by a higher dimensional barrier. Signals generated there wouldn't travel through space as we know it, but could leak across dimensional membranes, appearing abruptly in our reality before fading like a station drifting out of range. The WOW signal's bizarre properties, its narrow frequency, its sudden onset and disappearance, align eerily with this idea. It wasn't a deliberate broadcast from across the galaxy, but a fleeting cross-dimensional echo, a cosmic accident where realities briefly brushed against each other. The math behind this isn't as far-fetched as it sounds. In brane-world scenarios, our universe floats like a sheet of paper in a higher dimensional bulk, with other branes potentially mere millimeters away in a direction we can't perceive. Quantum fluctuations or gravitational waves in these neighboring branes could induce transient signals in our own, like ripples from a pebble dropped in a pond we can't see. Some theorists suggest such events might even leave distinct polarization patterns in radio waves, twists in the signal's orientation that natural astrophysical sources wouldn't produce. When researchers re-examined the WOW signal's limited data, they found hints of these anomalies, though the evidence remains frustratingly incomplete. Skeptics, of course, have other explanations: a rogue comet's hydrogen cloud, a glitching military satellite, or even terrestrial interference reflected off space debris could all mimic aspects of the signal. Yet none fully account for its intensity, frequency, or the fact that it appeared in a radio-quiet zone where natural cosmic noise is minimal. The higher dimensional hypothesis, while speculative, offers something unique, a framework where the signal's strangeness isn't a bug but a feature, a signature of physics operating beyond our perceptual limits. What makes this theory so thrilling isn't just solving a 40-year-old puzzle, it's the implication that our universe might be constantly humming with cross-dimensional chatter, most of it too faint or fleeting for us to notice. Future radio telescopes, like the Square Kilometre Array, could scan for similar signals with unprecedented sensitivity, hunting for patterns that defy conventional astrophysics. If they find repeats with the same peculiar fingerprints, it might not just confirm the WOW signal's origin, it could reveal that we're not alone in the cosmos, but surrounded by realities forever out of reach, occasionally flickering into view like distant lighthouses through dimensional fog. The truth may remain elusive, but the possibility lingers. That one summer night in 1977, we didn't just hear a whisper from the stars, we caught a glimpse through the cosmic keyhole into realms we're only beginning to imagine. And if we're right, the universe's greatest mysteries might not be written in the void of space, but in the hidden folds between dimensions, waiting for the right moment to make themselves known. On clear, moonless nights, long after sunset or just before dawn, a faint, ethereal glow sometimes rises from the horizon, a triangular smear of light stretching toward the stars. This is the zodiacal light, sunlight scattered by countless dust grains drifting through the inner solar system. For centuries, it was considered just a beautiful oddity, the celestial equivalent of dust motes caught in a sunbeam. But modern observations have revealed something strange. This cosmic dust cloud isn't behaving as it should. Its particles are too few, too large, and clustered in ways that defy conventional models. The numbers don't add up unless we're missing something fundamental. What if the discrepancy isn't a flaw in our calculations, but a clue that some of this dust isn't entirely of our dimension? Picture a spiderweb stretched across a doorway. From a distance, it looks flat, two-dimensional, but get closer, and you realize its threads extend in depth, vibrating with movements you couldn't see before. The zodiacal dust might be doing something similar. Certain string theory models suggest that higher dimensional particles could leave shadows in our three-dimensional space, not quite here, not quite gone, interacting with sunlight just enough to scatter it oddly. These wouldn't be ordinary dust grains, but higher dimensional objects brushing against our reality, their full structure curled up in directions we can't perceive. The result, a glow that's slightly too bright in certain wavelengths, or clustered in patterns that make no sense for ordinary comet debris. The anomalies are subtle but persistent. Space probes like NASA Juno have measured the zodiacal light with unprecedented precision. revealing unexpected infrared signatures, hints that some particles absorb and re-emit sunlight in ways that shouldn't be possible for simple silicates or carbon-rich dust. Then there's the dust distribution. Traditional models assume it's smoothly spread along the ecliptic plane, but observations show puzzling knots and voids, as if invisible fingers are stirring the cloud. One radical explanation: gravitational wakes from higher dimensional structures warping the dust's trajectory, like rocks in a river diverting the current. Skeptics argue there are mundane fixes: undiscovered asteroid families, interstellar dust intruders, or even measurement errors. But the higher dimensional hypothesis offers something compelling: testable predictions. If hidden dimensions are at play, the zodiacal light should exhibit specific polarization patterns, twists in the scattered light's orientation that betray unseen geometry. Future missions like the European Space Agency's Ariel telescope could hunt for these fingerprints. Even ground-based observatories are joining the chase, using adaptive optics to tease out the glow's finest details. The implications stretch far beyond a pretty sky glow. If higher dimensional dust exists, it could solve one of astrophysics' quietest mysteries, where all the missing comet debris went. Our solar system's dust budget has never balanced. There's less material than there should be from millennia of comets shedding ice and rock. But if a fraction of that debris isn't gone, just displaced into extra dimensions, the math suddenly works. It's like realizing your missing socks didn't vanish, they're stuck between the washing machine's drum and a fold in reality you never noticed. What makes this theory so enchanting isn't just its audacity. It's the way it transforms a celestial curiosity into a potential window onto the universe's hidden architecture. The next time you spot that ghostly glow rising before dawn, consider this. You might not just be seeing scattered sunlight, but the faintest reflection of dimensions beyond our own, shimmering like a mirage at the edge of perception. And if we're right, the answers we're seeking aren't just written in the stars, they're hiding in the dust. The M drive is the rogue physicist's dream, a propulsion system that shouldn't work, yet in lab tests it seemingly does. Picture a sealed, cone-shaped chamber where microwaves bounce back and forth. According to conventional physics, this setup should go nowhere, like a person trying to move a car by pushing from the inside. Yet, in multiple experiments, the M drive produced tiny but measurable thrust without expelling any propellant, as if defying Newton's third law. The scientific community erupted in skepticism, and for good reason. If the results were real, they threatened to uproot centuries of established physics. But what if the explanation isn't a flaw in the experiments? What if the M drive's thrust is a side effect of forces leaking into our world from dimensions we can't see? Hidden dimensions could offer a loophole in this cosmic conundrum. Imagine the M drive not as a closed system, but as a leaky pipe. While it appears sealed in our three-dimensional space, its microwaves might be interacting with higher dimensional fields or particles, transferring momentum in ways that look impossible from our limited perspective. Some theories suggest that the drive's conical shape could resonate with quantum fluctuations in extra dimensions, creating asymmetric pressure, like a sail catching wind from a direction we can't point to. Others propose that the thrust isn't violating conservation of momentum at all, but redistributing it into hidden geometries, like a ball rolling off a table and vanishing into a fourth spatial dimension. Of course, the M drive's history is riddled with controversy. Major labs, including NASA Eagleworks, reported anomalous thrust, but the results were often marginal, buried in experimental noise. Critics argue that thermal expansion, magnetic interference, or even the Earth's rotation could mimic the effect. Yet the tantalizing possibility lingers. If even a fraction of the observed thrust stems from higher dimensional interactions, it would revolutionize not just propulsion, but our understanding of reality. Spacecraft could one day push off against hidden dimensions, enabling interstellar travel without the need for colossal fuel reserves. The real intrigue lies in how the M-drive forces us to confront the limits of our models. Science thrives on skepticism, but it also advances through anomalies, those stubborn data points that refuse to fit. Whether the M-drive is a measurement error or a dimensional doorway, its legacy is secure. It reminds us that the universe still has secrets tucked away in places we're only beginning to imagine. And sometimes the most controversial ideas are the ones that push us to look beyond the obvious, into the folds of reality we've yet to explore. The quantum eraser experiment is one of those rare moments in science that feels less like a discovery and more like the universe playing a trick on us. Imagine firing particles through a barrier with two slits, watching as they create an interference pattern on a screen behind it, a telltale sign that each particle behaves like a wave, passing through both slits at once. Now place a detector to observe which slit each particle actually goes through. Suddenly, the interference pattern vanishes. The particles, as if embarrassed to be caught, start behaving like discrete objects. But here's where it gets truly bizarre. If you erase that measurement information after the particles hit the screen, the interference pattern magically reappears. It's as if the particles retroactively decide whether they were waves or particles based on whether their future includes being observed. This isn't just quantum weirdness, it's a direct challenge to our understanding of cause and effect. Hidden dimensions might offer a way to make sense of this temporal paradox. Picture time not as a straight line, but as a sprawling, multidimensional landscape where past, present, and future are interconnected like threads in a tapestry. In this framework, the act of observation in the present could send ripples backward through higher dimensional pathways, altering what happened in the past. Think of it like dropping a pebble into a pond, except the ripples move backward in time, changing the initial splash. Some interpretations of string theory suggest that quantum particles aren't confined to our linear experience of time. They might exist in states that span multiple temporal dimensions, allowing future choices to reach back and influence earlier events. This idea of retrocausality isn't just philosophical speculation. Experiments with delayed choice quantum erasers have consistently shown that the decision to measure or erase information after a particle's journey can determine its behavior before the measurement occurs. It's as if the universe is running on a script that's only finalized once all possible observations are accounted for. Hidden dimensions could provide the backstage where this editing happens, a higher dimensional workspace where cause and effect are more fluid, and the timeline is more like a rough draft than a finished novel. The implications are staggering. If retrocausality is real, it might mean that the universe doesn't just remember the past, it adjusts it. This could explain why quantum systems seem to know about future measurements, adapting their behavior in ways that defy classical logic. Some theorists even suggest that consciousness itself might play a role, with observers shaping reality not just in the present but across time. It's a humbling thought. Our choices today might not just shape tomorrow but rewrite yesterday. Of course, skeptics argue that retrocausality is a misinterpretation, that quantum systems are simply probabilistic, and the appearance of backward in-time influence is just a quirk of statistics. But the quantum eraser experiment keeps pulling us back to the same unsettling conclusion. Time might not be the one-way street we thought it was, and if hidden dimensions are the key to unlocking this mystery, they're not just hidden in space, they're woven into the very fabric of time itself, waiting for us to untangle their secrets. The beauty of this theory isn't just in its audacity, but in the way it forces us to rethink everything we thought we knew about reality. Whether retrocausality holds up or not, the quantum eraser has already done its job. It's erased our certainty, leaving us with a universe far stranger and far more interconnected than we ever imagined. The Mandela Effect is one of those eerie phenomena that blurs the line between psychology and science fiction, where large groups of people vividly remember events or details that never happened. From misquoted movie lines like, "Luke, I am your father," it's actually, "No, I am your father," to the collective false memory of the Berenstain Bears being spelled Berenstein. These shared discrepancies feel too widespread to dismiss as simple forgetfulness. But what if these glitches in our collective memory aren't just quirks of the brain? What if they're fleeting glimpses into alternate dimensions where those details were real, and our timelines briefly brushed against them? At its core, the Mandela Effect taps into a profound question about the nature of reality. Most psychologists attribute it to confabulation, the brain's tendency to fill gaps in memory with plausible fabrications, reinforced by social contagion. Once one person misremembers something, others unconsciously adopt that version, creating a snowball effect. But the dimensional overlap theory offers a wilder possibility, that some of these false memories are actually accurate recollections of alternate realities. Imagine a multiverse where every decision branches into new timelines, some nearly identical to ours, others subtly different. If the boundaries between these timelines occasionally fray, information could leak across, leaving some of us with residual memories of events that never occurred here but did happen there. The idea gains traction when you consider quantum mechanics. In the many worlds interpretation, every quantum event spawns parallel universes, each with its own version of history. Normally, these worlds remain separate, but if higher dimensions exist, they might intersect in ways we don't yet understand. Think of it like radio interference. Two stations broadcasting on similar frequencies sometimes bleed into each other, creating momentary overlaps. If consciousness itself is somehow entangled across dimensions, shared, false memories could be the static from those cross-dimensional signals. Skeptics, of course, point out that human memory is notoriously unreliable. We reconstruct past events on the fly, blending facts with assumptions, suggestions, and even pop culture influences. The spelling of Berenstain might feel wrong because Stein is a more common suffix in names, making the correct version seem alien. Similarly, Luke, I am your father, is a more natural phrasing in conversation, even if it's technically incorrect. But the dimensional hypothesis refuses to fade entirely, partly because some Mandela effects are so oddly specific, like the vivid collective memory of a 1990s movie called Shazam starring Sinbad as a genie, despite no such film ever existing. Could there be a middle ground? Some researchers suggest that while most Mandela effects are psychological, a handful might defy conventional explanation, acting as potential signposts to deeper physics. Future experiments in quantum consciousness or advances in multiverse theory might one day provide tools to test this. Until then, the Mandela Effect remains a tantalizing mystery, one that challenges us to wonder whether our memories are purely personal, or if they're sometimes windows into worlds just beyond our reach. And if that's true, the next time someone insists the Monopoly man definitely had a monocle, maybe the truth isn't in our heads, but in the hidden folds of reality itself. The hunt for hidden dimensions is no longer confined to chalkboards and thought experiments. It's playing out in real time, inside some of the most advanced laboratories and observatories on Earth. Imagine a world where gravity's secrets are teased apart by lasers so precise they can detect a distortion smaller than an atom's width. or where ripples in space-time, born from cataclysmic collisions billions of years ago, carry whispers of dimensions beyond our perception. This isn't science fiction, it's the cutting edge of physics, and the tools we're building today could crack the cosmic code within our lifetimes. Take atom interferometry, for example. Picture a cloud of ultra-cold atoms, chilled to near absolute zero, dropped inside a vacuum chamber. As these atoms fall, they're split by laser pulses, creating overlapping quantum waves that behave like microscopic pendulums. Any subtle change in gravity, say, from an extra dimension warping the local fabric of space, would nudge these waves out of sync, leaving a detectable fingerprint. Experiments like MAGI's 100 and Aeon are pushing this technology to unprecedented sensitivity, turning individual atoms into probes for the universe's hidden architecture. It's like using a feather to measure the breath of a ghost, except the ghost might be gravity itself, slipping between dimensions we've yet to map. Meanwhile, gravitational wave astronomy has evolved from a niche field to a cosmic listening post. When black holes merge, they don't just send ripples through space-time, they might also vibrate the higher dimensional bulk surrounding our universe. Next-generation detectors like LISA, a space-based observatory set to launch in the 2030s, could catch these multidimensional echoes. Imagine dropping a pebble into a pond and seeing not just the splash, but the faintest hint of a second, smaller splash from a parallel pond beneath the surface. That's the kind of subtlety physicists are hunting for, anomalies in gravitational wave patterns that betray the presence of unseen dimensions. But the most revolutionary tool might be quantum sensors. These devices exploit the bizarre rules of quantum mechanics to measure forces with unreal precision. Some prototypes can detect gravitational shifts caused by a person walking nearby, or theoretically, by higher dimensional fields brushing against our reality. Projects like the Fermilab holometer and quantum compasses under development for navigation are accidentally becoming dimension hunting machines. They weren't built to find extra dimensions, but their sensitivity is so extreme they might stumble upon them anyway. It's like building a microphone to hear a whisper, only to discover it can also pick up conversations happening in another room, one separated from ours by a wall we didn't know existed. The stakes couldn't be higher. If these experiments find evidence of hidden dimensions, it would rank among the greatest scientific breakthroughs in history, a paradigm shift on par with relativity or quantum mechanics. But if they come up empty after a decade of searching, physicists might need to face an even more unsettling possibility: that the math we've trusted for clues is leading us astray, and reality's deepest secrets are hiding in places we've yet to imagine. Either way, the next chapter of this story won't be written in equations alone, but in the hum of lasers, the shudder of detectors, and the quiet persistence of those who dare to ask, what if there's more to the universe than meets the eye? And if we're right, the answers won't just redefine physics, they'll redefine what it means to explore. The age of discovery isn't over. It's just beginning to peer beyond the dimensions we thought were all there was. From string theory's elegant dimensions to the wild possibilities of brains and holograms, these 40 theories paint a universe far stranger than we ever dared to imagine. Hidden dimensions aren't just the stuff of science fiction, they're serious science, with the potential to rewrite everything we thought we knew about reality. Think about it, every time we've peeled back a layer of the cosmos, from the atom to the quantum foam, we've uncovered deeper, more bewildering truths. The idea that we might be standing on the threshold of another such revolution, one that reveals the very fabric of space and time, is woven with dimensions beyond our perception, is nothing short of exhilarating. What makes this search so compelling isn't just the promise of discovery, but the sheer audacity of the questions it forces us to ask. Are we living in a cosmic hologram with the true nature of reality encoded on a distant, two-dimensional surface? Could black holes be gateways to other universes, their singularities bending into dimensions we can't see? And if dark matter is really matter vibrating in directions we can't point to, what else might be lurking just beyond our grasp? These aren't abstract musings, they're hypotheses being tested right now in labs and observatories around the world. The fact that we're even asking them is a testament to how far we've come. Experiments are inching us closer to answers. Particle colliders like the Large Hadron Collider are hunting for microscopic black holes or missing energy that could betray extra dimensions. Gravitational wave detectors are listening for echoes of higher dimensional ripples in the aftermath of cosmic collisions. Even tabletop experiments with ultra-cold atoms or quantum sensors are probing gravity at scales so tiny, any deviation from Newton's laws could hint at hidden geometry. It's a global effort spanning disciplines and technologies, all aimed at uncovering what the universe has been hiding in plain sight. But here's the most thrilling part: we don't know what we'll find. The universe has a habit of surprising us, often in ways we least expect. The discovery of hidden dimensions could come as a whisper, a subtle anomaly in a dataset, or as a thunderclap upending centuries of physics overnight. Either way, the implications would be profound, unifying gravity and quantum mechanics, explaining dark energy's mysterious push, even unlocking the possibility of traversable wormholes. All of it could be within reach if we crack the code of higher dimensions. Yet, even if the experiments come up empty, the journey is worth it. The pursuit of hidden dimensions has already reshaped our understanding of reality, pushing the boundaries of math, physics, and philosophy. It's reminded us that the universe is under no obligation to make sense to us. We have to meet it on its terms with curiosity and humility. And that's the real beauty of science, not just the answers, but the questions that keep us reaching further. So as we stand on the edge of this new frontier, the best thing we can do is stay open to the possibilities. Keep questioning, keep exploring, because whether hidden dimensions are confirmed tomorrow or remain elusive for centuries, one thing is certain: the cosmos is far grander, far weirder, and far more wondrous than we've yet imagined. And the adventure of uncovering its secrets, that's just beginning. Which of these mind-bending theories left you rethinking reality? Was it the holographic principle turning our universe into a cosmic projection? The spine-tingling possibility that black holes are higher dimensional portals? Or the radical idea that dark matter might just be ordinary matter vibrating in directions we can't point to? This journey through hidden dimensions has peeled back layers of reality you never knew existed, but here's the wildest part: we've barely scratched the surface. The universe still holds countless mysteries waiting to be unraveled, and your curiosity is what drives these discoveries forward. So let's keep the conversation going. Drop your favorite theory in the comments below. Did the brane-world collision hypothesis rewrite how you see the Big Bang? Are you still wrapping your head around retrocausality in the quantum eraser experiment? Every perspective adds another piece to this cosmic puzzle, and if you've got a wild theory of your own, share it. Some of history's biggest breakthroughs started as what-if moments between curious minds. Make sure to hit that like button if these ideas electrified your imagination. It helps more explorers join this adventure. And subscribe so you don't miss our next deep dive into the universe's best-kept secrets. From time crystals bending the rules of physics to the eerie Mandela Effect hinting at dimensional overlaps, we're just getting started. The cosmos is stranger than fiction, and together we're uncovering its hidden blueprints, one mind-blowing revelation at a time. The greatest discoveries begin with a single question: what's yours? Let's find